Welcome to the Machine Learning Specialization and this first course on the fundamentals of machine learning. We're really excited to embark on this journey with you. Right, B?
We are. Are you going to say who you are?
Oh, I'm Carlos.
And I'm Emily.
And together we're going to learn about applications of machine learning, how to build machine learning systems, and how the algorithms behind them work, and how to build those algorithms.
We're clearly just so excited about this course and this specialization, we can barely put the words together to describe it.
So let's get going. Hi, I'm Carlos Gaston. I'm the Amazon Professor of Machine Learning.
Wait, I'm the Amazon Professor of Machine Learning.
Who are you?
I'm Emily Fox.
Well, I'm the Amazon Professor of Machine Learning in Computer Science.
And I'm the Amazon Professor of Machine Learning in Statistics.
We're both at the University of Washington in Seattle. This is the United States.
This is the United States of America.
Of America.
To clarify.
America. So, what are your qualifications to be here today, Emily?
Am I supposed to read my CV? No. Okay. Just the beginning of it. What are my qualifications? Okay. Well, I went to MIT for way too long, 9 years, though it wasn't all for one degree. Got a couple of them during those 9 years. But yeah, I was there for my PhD, studying in electrical engineering and computer science. Should I list more qualifications? I think that's pretty good.
She's very well qualified. Let me just say that. And I got my undergrad from University of São Paulo in Brazil, and my PhD from Stanford in computer science. And I've been working in machine learning for a long time, as Emily likes to say.
A very long time. I guess maybe I should describe a little bit about my transition to statistics. So after I did my PhD in electrical engineering and computer science, I did a postdoc in statistics at Duke. And actually, honestly, a lot of my PhD really was a statistics PhD, but MIT, as of the time of this recording, does not have a statistics department, and did not at the time that I studied there. So, yes, I'm a self-taught statistician.
And we can all be self-taught.
Yes. That's what this MOOC is about.
Hey, we're learning together. So I've been working in machine learning for a while, and I'm really excited about methods in machine learning from a wide range of settings. I've worked on theoretical algorithms for what's called planning under uncertainty, for making decisions using machine learning. I've worked with sensor data, with distributed sensors, something called sensor networks, which today is called Internet of Things, but this is way back. And then I took a big focus on large-scale machine learning. So how do you scale up machine learning methods to lots and lots and lots of data? And we'll use some of these ideas in this specialization as well. How about you?
I don't have quite as long of a history as Carlos does. But the things that I really enjoy working on are time series applications, so data that comes in over time, and we want to find some underlying structure or patterns to that data. And a lot of my focus in my research is on how to scale up to really high-dimensional or large collections of time series, especially when they have very complex dynamics. And another one of my big interests is how to make inferences online as data is streaming in. And I've worked on a wide range of different applications, some that I'm really passionate about. One in particular right now is neuroscience, but I've also worked on speech data, motion capture applications, analyzing human motion, to financial data, and the list goes on and on. But lots of data have really important temporal structure, and that's really a passion of mine. And
we've been teaching machine learning for a long time, mainly in the university
Some of us
setting.
longer than others.
This joke never ends.
No.
Mainly at the university setting. So here we are. It's an exciting experience for us to teach in this online course.
Yes.
So how did you decide to do this online course?
How did I decide? That's a very good question. Well, no, there are a lot of reasons why I wanted to do this online course, but really the most fundamental reason was thinking about how to disseminate machine learning to a very broad audience, because personally I came from a very different background and training, and actually Carlos did as well. And so I myself have gone through this experience of trying to learn machine learning, learn statistics, and I think there's a really nice way that it can be taught at a very fundamental level to a very broad audience. And that's one of my passions. And another reason is I'd like to think about this for other goals in the future of how to convey this to other groups that I interact with on campus as a teacher at the University of Washington, professor, assistant.
Not for long. So, yeah, and I'm very excited about how machine learning gets taught. And we really have been thinking a lot about how to approach kind of this really broad idea of machine learning in a new way. So in this specialization, as we'll talk more about in this module, you're going to experience machine learning in a whole different way than you experience in other places. We're really going to be focused on applications first, understanding how machine learning has impact, and then digging in and understanding how those methods are built and how they can be useful. So part of the journey for us is to build a new way to teach machine learning, which is cool.
It is cool.
So very exciting.
Yes, we're excited.
I've been doing machine learning for a long time, and it's a really exciting time to be doing machine learning today because we're really seeing a lot of impact from it. But this is not how I started machine learning. If you just talked to me a few years ago, the way I thought about machine learning was quite different. You started with some data set, some data, and you fed it to some magical machine learning algorithm, and then I just showed you that my curve was better than your curve, and then I wrote a paper to a machine learning conference. And that's how I always thought about machine learning. But this is not why I got into the first place. Why did I get into machine learning? When I was a kid, I read a lot of books, a lot of sci-fi, and I really wanted to build robots that were really intelligent, that really thought about the world and reasoned about things. What I call today intelligent applications. And the really cool and exciting thing is that today we're seeing a lot of impact from intelligent applications that are using machine learning. In fact, if you look at industry after industry, successful companies today, companies that are called disruptive, that take a market and completely change it, they're often differentiated by intelligent applications, by intelligence that uses machine learning at its core. So for example, early days, Amazon really disrupted the retail market by bringing in product recommendations into their website. We saw Google disrupting the advertising market by really targeting advertising with machine learning under it to figure out what people would click on. You saw Netflix, the movie distribution company, really change how movies are seen. We don't go to a shop and rent movies anymore. We go to the web and we stream data. Netflix really changed that, and at the core there was a recommender system that helped me find the movies that I liked, the movies that were good for me, out of the many thousands of movies they were serving. You see companies like Pandora, where they're providing a music system, a music recommendation system where I find music that I like and I find streams that are good for the morning when I'm sleepy, or at night when I'm ready to go to bed and I want to listen to different music, and they really find good music for us. And you see that in many places, in many industries. You see Facebook connecting me with people who I might want to be friends with, and you even see companies like Uber disrupting the taxi industry by really optimizing how to connect drivers with people in real time. So in all of these areas, machine learning is one of the core technologies, the technology that makes that company's product really special. So in this specialization, we're really going to talk about all aspects of machine learning and get you ready to build intelligent applications just like that. And we're going to see a pipeline again and again and again, where we're going to start from data and really bring in a machine learning method that provides you with a new kind of analysis in the data. And that analysis is going to give you intelligence. Intelligence like, what product am I likely to buy right now? And by taking this pipeline and working through it in a wide range of settings, in a wide range of applications, with a range of algorithms, but really understanding how they connect together, you're going to be able to really build smart, intelligent applications of your own.
So the way we're going to learn about this data to intelligence pipeline is by examining a number of case studies that are going to ground the methods that we present in real-world applications. And that's one of the really unique features of this course. In our first case study, we're going to look at predicting house values. So the intelligence we're deriving is a value associated with some house that's not on the market. So we don't know what its value is, and we want to learn that from data. And what's our data? Well, in this case, we're going to look at other houses and look at their house sales prices to inform the house value of this house we're interested in. And in addition to the sales prices, we're going to look at other features of the houses, like how many bedrooms the houses have, bathrooms, number of square feet, and so on. And what we're going to do, our machine learning method, is something that's going to relate the house attributes to the sales price. Because if we can learn this model, this relationship from our house level features to the observed sales price, then we can use that for predicting on this new house. We take its house attributes and predict its house sales price. And this method is called regression. In our second case study, we're going to explore a sentiment analysis task where we have reviews of some restaurants. So for example, in this case, it says, the sushi was awesome, the food was awesome, but the service was awful. And we want to take this review and be able to classify whether it had positive sentiment, it was a good review, thumbs up, or a negative sentiment, thumbs down. And so how are we going to do this? Well, we're going to look at a lot of other reviews. So we're going to look at the text of the review and the rating of the review in order to understand what's the relationship here for classification of this sentiment. So for example, in this case, maybe we might analyze the text of this review in terms of how many times it uses the word awesome versus how many times it uses the word awful. And from these other reviews that we have, we're going to learn some decision boundary based on the balance of usage of these words, whether it's a positive or negative review. And the way we learn that from these other reviews is based on the ratings associated with that text. And so this method is called a classification method. In our third case study, we're going to do a document retrieval task, where here, what we want to do, the intelligence we're deriving is an article or a book or something like this that's of interest to a reader. And the data that we have is a huge collection of possible articles that we could recommend. And what we're going to do in this case is we're going to try and find structure in this data based on groups of related articles, such as maybe there's a collection of articles about sports and world news and entertainment and science. And if we find this structure and annotate our corpus, our collection of documents with these types of labels, which we don't have ahead of time, we're trying to infer this from the data, then we can use this for very rapid document retrieval. Because if I'm sitting here currently reading some article about world news, then maybe if I want to retrieve another article, I already know which articles to search over. And this type of approach is called clustering. In our fourth case study, we're going to do this really interesting thing that's called collaborative filtering that's had a lot of impact in many domains in the last decade. Specifically, we're going to look at doing product recommendation, where you take your past purchases and try and use those to recommend some set of other products you might be interested in purchasing. So in this case, the data that we're going to use to derive this intelligence for product recommendation is we'd like to understand, well, what's the relationship between what you bought before and what you're likely to buy in the future? And to do this, we're going to use other users' purchase histories and possibly features of those users. But the key idea here is we're going to take this data and we're going to arrange it into this customers by products matrix, where the squares here indicate products that a customer actually purchased. So those are products that are liked by that customer. And from this matrix, we're going to learn features about users and features about products. And once we learn those features about users and products from this data that I've described, we can think about using those features to see how much agreement there is between what the user likes, different attributes the user likes, and whether the product is actually about those attributes. So in the example I'm showing here, maybe a user is a mom, has certain features that are similar to other users that are also moms, and from that we can infer things about products, what are attributes about, for example, baby products that are of interest to moms. And we're using that information to form our recommendations. And this type of approach, going from this matrix, this customers by products matrix, into these learned features about users and products, is called matrix factorization. Okay, well, in our final case study, we're going to look at a visual product recommender. So here, our data is somebody's going to go to the web and they're going to input not text, but an image. They're going to input an image like of a black shoe or a black boot or a high heel or some Docker shoe or a running shoe. And what they want is they want a set of results of shoes that might also be of interest to them. So shoes that are visually similar to the picture that they have. And they want to be able to search over those to purchase this item. And the way we're going to do this, to be able to go from an image to a set of related images, is we need to have very good features about that image to find other images that are similar. And the way we're going to derive those really detailed features is something called deep learning. So in particular, we're going to look at these neural networks where every layer of the neural network provides more and more descriptive features. So in the little example we show here, the first layer might just detect in the image things like different edges. Whereas when we get to the second layer, we start detecting corners and more interesting features like that. And as you go deeper and deeper in these layers, you get more intricate features arising. So as you see, we're going to walk through a series of real-world case studies, real-world problems, and real-world solutions using machine learning. And through this, we're going to explore a series of methods that have a lot of power out there and are going to allow you to be able to develop and deploy new machine learning techniques on new problems that aren't the exact case studies we used, but the case studies will allow us to really ground the methods that we're describing with things that are very interpretable.
As Emily discussed, we're going to see machine learning through the lens of a wide range of case studies in different areas that really ground the concepts behind it. So other machine learning classes that you might take out there are really a laundry list of algorithms and methods. So things like support vector machines and kernels and logistic regression and networks and so on. And they're just like a laundry list of methods. And the problem with that approach is that since you start from the algorithms, you end up with really simplistic use cases or applications that are really disconnected from reality. So we're doing things very different in the specialization. And we've done this for quite a while here. Emily and I created a course at the University of Washington on machine learning at scale for big data, where we pioneered this use case approach for teaching machine learning. And in that course, we saw a lot of positive feedback from folks really understanding and grounding the concepts. So we're going to start from the use cases in the first course. And by starting from use cases, you're really going to be able to grasp the key concepts and the techniques that allow you to build, measure the quality, and understand whether your intelligent application is working well or not. And in the end, you're going to build a bunch of these intelligent applications. So to build such intelligent applications, you typically have to think about what task am I going to do? I'm going to solve a sentiment analysis problem. And what models, what machine learning models am I going to use? There are things like support vector machines or logistic regression, and what methods I'm going to use to optimize the parameters of that model. And then I ask a question like, is this really providing the intelligence that I'm hoping for? How do we measure the quality of that system? So in this specialization, what we're going to do is defer the core pieces of how to describe a model and optimize it to the follow-on courses. And this first course is going to be focused on helping us figure out what tasks we're trying to solve, what machine learning methods make sense, and how to measure them. And with that, using the algorithms as black boxes, we're going to be able to build a wide range of really intelligent, cool applications together. And we'll actually code them and build them and demonstrate them in a wide range of ways. Now, the following courses, they're It's going to be 4 of those plus a capstone that really go into depth in different areas. So let me give you a few quick examples of what quite kind of depth we're going to see throughout the specialization. So the regression course is going to talk about various models of predicting a real value. So for example, a house price from the features of the house. And we're going to discuss linear regression techniques. We're going to discuss advanced techniques like ridge regression and lasso that allow you to select what features are most appropriate for your problem. We're going to talk about optimization techniques like gradient descent and coordinate descent to optimize the parameters of those models, as well as some key machine learning concepts like loss functions, bias variance trade-offs, cross-validation, things that you need to know to really take these methods and kind of improve them, develop them, and build applications with them. The second course on classification, we're going to build, for example, the sentiment analysis use case that Emily talked about, and talk about models for classifications, from linear classifiers to more advanced things like, linear regression, logistic regression, support vector machines, but then add kernels and decision trees, which allow you to deal with non-linear complex features. We talk about optimization methods for dealing with these techniques at scale, and for building ensembles of them, something called boosting, and then the underlying concepts in machine learning that really help you grasp a classifier and scale it up and apply it to different methods. Now, in the next course, we're going to focus on clustering and retrieval, especially in the context of documents. So we're going to talk about basic techniques like nearest neighbors, as well as more advanced clustering techniques, mixture Gaussians, and even latent Dirichlet allocation, kind of advanced text analysis clustering technique. We're going to talk about the algorithms that underpin these things and how to scale them up with techniques like KD trees and sampling and expectation maximization. Now, the core concepts here are really around how to scale these things up, how to measure the quality, and really how to write them as distributed algorithms using techniques like MapReduce, which are implemented in systems like Hadoop that you might have learned about. So in the fourth course, you're actually going to write some MapReduce code for distributed machine learning. Now, in the final technical course, we're going to focus on techniques of matrix factorization and dimensionality reduction, which are widely applicable, but in particular for recommender systems or for recommending products. So these are things like collaborative filtering, matrix factorization, PCA, and the underlying techniques for optimizing them, like coordinate descent, eigenvalue decomposition, SVD, and then a wide variety of core machine learning concepts that are really useful, especially in the recommenders domain, like how to pick a diverse set of recommendations and how to scale them up to large problems. Now, the capstone is going to be really exciting, and towards the end of this module, I'm going to go back and tell you quite a bit more about the capstone, but just to give you kind of a little hint, you're going to build something extremely cool that you can show to all your friends, potential employers, and you'll see that you can build a really smart, intelligent application around recommenders that combines text data, image data, sentiment analysis, deep learning. It's going to be really cool.
So how did you get into machine learning?
It's interesting. So as I talked about earlier in the module, I started because I really cared about robots. I really wanted to build robots, and I thought, okay, the way to build robots is to do mechanical engineering. And so I started with mechanical engineering, and then I realized, the hard thing about building robots is the robot brains, and that took me into computer science. And then I realized that a hard part of AI was understanding data, and that got me into machine learning. So I did my PhD in machine learning. So that's a journey from thinking about robots all the way to becoming somebody excited about data and about machine learning. So how about you?
Similar but different journey. I wasn't sitting there raising Isaac Asimov, making these lifetime aspirations to build robots, but eventually I actually was working with robots. But the thing that really got me into machine learning is I was working on this target tracking application where we're trying to track these really highly evasive vehicles like a plane. So a plane's flying and makes some maneuver to try and avoid being tracked. But the issue is that the systems were really, really highly engineered to assuming that you knew the physics of this airplane, that you knew that it was going to do some kind of turn right maneuver and turn left, and this is how the physics are when the plane is flying straight or landing or things like this. And so you would build these models that were known based on physics of the system, all these different modes. But what would happen is the plane would do something that we hadn't seen before, and the system would try to accommodate for it by saying, oh, well, it's just rapidly switching between turn right, turn left, turn right, turn left. But of course, that didn't actually describe what was going on. So I thought there must be some better way to actually learn the parameters of the models that we're trying to deploy, and somehow capture uncertainty about how much we actually believe in the model that we've specified, to be a bit more robust to these types of situations. So that's what got me into machine learning and statistics.
Right. So as you can see, I came from mechanical engineering and got into data, into machine learning, and came from electrical engineering and tracking planes and got into machine learning. But today it's really exciting because we're seeing people from all sorts of fields get into machine learning. We see physicists excited about data. We see people in biology,
social sciences, philosophy,
all sorts of places, math, reinventing self, statistics, computer science. All the
art. You always like to mention art.
Art, yeah. When I taught at Carnegie Mellon, there was even some art students that took my machine learning class, and they're building really cool art installations that use machine learning inside them, which was really quite amazing. We even taught a class there with my friend Osman Khan on building art installations that use machine learning. So we see a variety of people with different backgrounds, just changing their lives, thinking about data science, thinking about machine learning, and building intelligent applications. And they all have a passion for data, which is cool.
It is cool. That's how we're going to end every one of these chats. That's cool. It is cool.
It is cool.
See you next chat.
Cool.
Let's take a little pause and spend some time talking about who the specialization is geared for. Well, the first thing I want to emphasize is the level of the specialization. And what we're going to do here is we're going to teach you really important machine learning methods, but we're going to ground them in real-world applications like we saw with our case studies. So a motto that we have here is tough concepts made intuitive and applicable. So this course isn't going to be about theorem proving. It's going to be about understanding at a very intuitive and practical level some very important machine learning algorithms and thinking about ways in which to deploy them in new problems. And when we're going about this, our goals here are to minimize the amount of prerequisite knowledge that you have to understand what we're presenting, while maximizing the ability for you to actually develop and deploy these methods on new problems that are of interest to you. And when we're thinking about this, we're going to be presenting concepts at this very intuitive level that's grounded in these case studies. So who might you be? Well, when we're thinking about the target audience, we're thinking about software engineers who are interested in machine learning. We're thinking about scientists who might want to become data scientists. And we're thinking about lots and lots and lots of other people who have some math, some programming experience, and want to be able to analyze data and do fun things with it. So just data enthusiasts who want to learn more about machine learning and how to derive intelligence from data. Okay, so I said that we're assuming you have some math and some programming background. So let's talk about this in a little bit more detail. In terms of the math background, we're assuming that you have some basic calculus knowledge. So that's understanding the notion of derivatives and how they're computed, and basic linear algebra. So you guys should know what a vector is, what a matrix is, and how to multiply matrices. But in these cases, we're really, as often as possible, going to present things at the most intuitive level. Even if we could write down an equation in terms of matrices and matrix multiplies, we're going to try and add as many visual aids as possible to provide you with that intuition, so that if you're only marginally comfortable with these ideas, I do suggest that you go brush up on these concepts. But again, we're going to try and provide the intuition that we described as part of our motto. And in terms of programming experience, In this specialization, we're going to be using basic basic Python for programming. But if you're not familiar with Python, it would, of course, be helpful if you were familiar with basic Python. But we think that you can pick up on the important tools that you'll need if you have some other knowledge of some other language. Okay, so finally, what are your computing needs for this course? Well, we're going to assume that you have some basic desktop or laptop or access to one where you can access the internet. Of course, that's important, so you can watch these lovely videos. But beyond that, so you can do your assignments, and to do your assignments, you're going to need to be able to install and run Python. And in addition, you're going to have to be able to store a few gigabytes of data. Okay, so that basically summarizes what we have in mind for who this specialization is for, and we hope that fits your case.
Now that you've seen what this course is going to be about, as well as a specialization as a whole, you'll see that you'll be able to do amazing things using machine learning, build really intelligent applications as you go through this process. Not just at the end, but throughout the whole specialization, you'll be building cool stuff, and you'll be learning about a wide range of concepts and building their algorithms. So the first course is really about using those pre-built machine learning algorithms to build a range of intelligent applications. Now, the follow-up courses, the second through the fifth, takes different areas and really goes in depth, talks about the algorithms, the methods, the techniques behind it. Now, let's go back and talk about the capstone. The capstone is going to be really exciting. You're going to build a really cool, impressive application that uses machine learning. Let's dig in and talk a little bit about that capstone application that we're going to build together. So we're going to build a recommender system for products that's intelligent, that combines text, images, sentiment analysis, and deep learning. Now, before talking about the capstone project, which is really going to be exciting, let me give you a quick demo of something that you could build, a recommender system that you could build that combines text and image data and uses deep learning at its core. Now, let me show you an example of an intelligent application for recommending products that combines image and text data and uses deep learning at its core. So let me start with a story. So my sister is a fashion designer, and her birthday is coming up this month, and I wanted to get her a gift that would impress her, and I wanted to get her a dress. But it's really hard for me to choose a good dress. I don't know that much about dresses. So if I do just standard keyword search and I search for dresses, I'm going to end up with something that looks like this that I'm showing you on the right here. And you'll see there's a wide range of dresses, and it's very hard for me to describe the kind of dress that my sister likes. And so I've seen her, for example, wear some floral dresses. So I could do a keyword search that combines the keywords dress and floral and looks through the description of the dress and try to find some floral dresses. But even within floral dresses, you see that there is a wide range of floral dresses up there, and each one of them has a pretty different kind of style. So the question is, how can I describe what is a good style for my sister? Now, for example, take this dress over here. It looks a little bit like what you might like. It's warm sunset colors and rich. So there's some text analysis that we can do that shows you a little bit about what describes this dress, but really visually it looks good. So the question is, can we use visual cues to find other dresses that look kind of like this one? And you do things like this in your capstone project. When I click on this dress, we're going to find visually similar dresses using a technique called deep learning that you're going to learn about already in this first course and apply it in practice. So when I click on this dress, what I'm going to see on the right is a bunch of dresses that are visually similar to this one. And you'll see, for example, the dresses tend to be floral, they tend to have the similar hues, similar colors, and even then it's hard to describe what my sister might like, but I can look at this dress right in the middle over here and say, wow, this has interesting pattern, different colors, maybe this is what my sister likes. And if I click on it, I'm going to find visually similar dresses to this one. So dresses have more interesting patterns and multiple colors associated with them. So you'll see as I scroll, there's various of these, and then maybe my eye catches this one over here, where it looks like something that my sister might like, and I might call her up and say, hey, I think I found a great dress for you, this one. Now, let's say that I call my sister, and she looks kind of like this model. I call her up, and she says, this looks okay, but I'm going to a cocktail party, and why don't you get me a cocktail dress? So I'm trying to think about, I start over, and I'm going to try to find her a cocktail dress. So cocktail dresses are ones that you wear for more formal parties. They look kind of like this, and there's all sorts of colors and things, but maybe she's interested in a black cocktail dress. So just based on keyword search like black cocktail dress, you'll get things like this, but it's hard to describe what my sister might be interested in. So I might ask her, what you're interested in? She says, what I'm interested in is a cocktail dress that's interesting with a touch of color. She's a fashion designer. What do I do? How do I describe that? So I look for this and say, well, this first here on the left is kind of interesting. If you look at the keywords associated with it, you see the keyword jazzy. So maybe she's interested in a jazzy dress. So what do jazzy dresses look like? So when I click on this keyword that I discovered from the text, you'll see other jazzy dresses, and they're kind of interesting, but they're not exactly kind of cocktail dresses. So let me just click on this one and find a visually similar cocktail dress. Now what you see is a bunch of cocktail dresses that tend to have a bit more of interesting patterns associated with them. So they're more interesting, more along the lines of what she was describing. So if I scroll through this, say, okay, this looks pretty cool. Maybe this one on the center, which is blue, maybe has some color to it, is what she's looking for. I click on it. I figure out, what? It's not formal enough for a cocktail dress. But if I scan down, you'll see that I can find a dress like this one, where it's a cocktail dress, it's formal enough, it has a touch of color to it, and it's interesting. And it might be something that you'll actually be interested in wearing. So here we've seen an intelligent application that looks at text data, image data, uses deep learning, and does some really cool and interesting things. So we saw this demo of deep learning for visual product recommendation. But in your capstone, you'll do something really even cooler, much more interesting than this. You're going to take your capstone project and you're going to combine a variety of things. You're going to buy recommenders. So you build a recommender system. You're going to do some text analysis, sentiment analysis, what people are saying in their reviews about different products, and extract those reviews and analyze them. You're going to do some computer vision to visually understand images. You're going to do some deep learning to really take that computer vision techniques and make them extremely accurate. And then you're going to take it and deploy it like a web service, like the one I just showed you, that web page. You're going to have your very own intelligent web service for products, which you can interact with, do some really interesting things, and really show to a ton of people how you created the intelligence behind that service.
Okay, so it's a really exciting time to do a machine learning specialization because we see machine learning everywhere in our everyday lives. So for example, Carlos is always on my case that I'm on my phone. So I turn on my phone and there are a lot of smart applications on here, and there are things that are personalized to me as a user.
And they're all using machine learning at their core, which is exciting. Today, every time you go to a website, most likely there's a machine learning algorithm behind the scenes analyzing the data, analyzing the interactions, and really changing your experience using machine learning. And we're seeing that in a wide range of settings.
Yeah, so not just on my phone. One device that Carlos loves is this thing.
It's a wearable device that tracks my activity, analyzes my sleep, analyzes my exercise routines, captures what I'm doing, and really takes that data, understands it, and helps me look at how my health is evolving over time, which is pretty cool.
So that's why it's exciting to think about machine learning now. But of course, there's a lot more that machine learning has the possibility of doing in our lives.
You can see the world changing with self-driving cars, with personalized medicine, with Internet of Things. We're embedding sensors everywhere, with smart systems everywhere. And so in this specialization, you're going to learn the fundamentals to do all of these things. In fact, after this specialization, you'll be future ready, future proof, or
future proof. You'll be
the future.
futurized.
You'll be the future of machine learning.
You are the future.
No.
And that is cool.
And that is cool. And in fact, you are the future because we recorded this in the past. So it's actually true. And that is also cool.
Clearly, Carlos is still watching and reading, mainly watching too much sci-fi.
Yeah. Did you see
You are in the future.
Did you see the latest season of Doctor Who? It's pretty cool. Anyway.
On that note, this is cool.
And it's going to be a really cool
specialization. You're supposed to say it is cool.
It is cool. And it's going to be a really cool specialization. And let's get started. Today we're going to talk about two really exciting tools for programming machine learning algorithms and also useful in data science. One is the Python programming language, and the other one is what's called the IPython notebook. At this point, I'll assume that you have already installed Python in your system. You've gone through those steps of installation. And now I'm just going to go over a few tips to get started. There's lots and lots of resources available online for you to explore and familiarize yourself with all the techniques that you need to do. But really, I think it would be fun for us to go over this together, since it's a really, really useful tool and something that makes a tremendous difference in practice. When you first call IPython notebook, you're faced with something like this. It's basically a version of your directory with all the files in the directory. There's some data files that I have, as well as some IPython notebooks I've created earlier, and some other data in that file. This is more like a file browser. So what we're going to do is just start a whole new notebook. So I'm going to go new, Python 2, since we're going to have a notebook that is a Python notebook. And welcome, this is IPython notebook. This tool has been around for a few years now, and it has really changed how we build machine learning and data science algorithms and how we communicate about them with others. It's really a useful tool. It blends two things that I love: Python, a simple scripting programming language, with wiki pages, things which make it really easy to communicate with others. So Python plus wiki pages is the IPython notebook. So today I'm going to both show you the IPython notebook and also going to show you some tips and tricks in Python just to get started, assuming that you can program in Python or in other programming languages. So you've run IPython notebook and you've started a fresh new one. Let me just walk you over the interface. So at the very top here is the title of the notebook, and we're going to change it to something else. So I'm going to change it to Getting Started with IPython Notebook. And there you go. We have a new notebook, and that's a title. And so this notebook is kind of like a console for Python, but it also allows you to save the page that you generate and include text and images in it. And we're going to play with all of that during this course because it's extremely useful. It has a menu here that allows you to do things like save the file that you have and load a new one, edit, copy, add new cells, and we're going to talk about those soon. But let's just get started. So let's get started with Python. I'm going to click on one of the cells, which is kind of like an entry in a console, and I'm going to type my first Python function. So the first function we're going to do is just print. So we're going to print a string, and strings in Python can be single quotes or double quotes, it's up to you. And the string we're going to print is the famous hello world. And when I press Shift Enter, it executes a cell. So you have to remember to press Shift Enter. We'll talk about pressing just Enter in a second. And after executed, it says hello world. So now let's take a ride on IPython notebook and some of the Python functions that we're interested in using during these courses. So the first piece of IPython notebook is that you can include text, and really well-formatted text. So there's two ways of accessing text cells. So the first one is to go over here to cell type, and call it markdown. And then you click on it and you can start writing. And it's really a markdown language, kind of like wiki pages. So if I put a pound here, I can do a header, getting started with Python. Oops. And now if I press, instead of pressing Shift Enter, just press regular Enter, it gives you a multi-line cell. So Enter, let's get started with Python, and let's do a subheader now. The first thing that we're going to assume is what you have done so far. So we have done the following. So just press Enter. Here's a list. We've installed Python, the Python programming language. We've started IPython notebook, and okay, so that did not work so well. Okay, I executed it, it's not quite right. Let me see what I forgot. So I can double click on it and edit. I forgot to put a space here. So space between the different lines. So we've installed IPython and we started the IPython notebook. This is what we've done so far. And now if I press Shift Enter, and you can see now we have a list. So we've done those things. I'm going to go continue editing. So I double click again. And now next, what we're going to do is create some variables in Python. Shift Enter. And now we're back to the next cell. Now, Python is a scripting programming language, just like many other scripting languages right out there, which makes it really easy to prototype things. And what we'll also see today is some machine learning tools that make it easy to run machine learning algorithms at scale, even within the simple programming language like Python. But for now, let's just start with the simple programming language. So Python is a scripting language, and you can create variables as you go. You don't have to declare them formally, and you don't have to declare their types. So for example, if I say I is equal to 4, what I get out of this is an integer, as we'll see. So comments in Python can be done in various ways. So for example, I can put just a pound sign here, int, and just to tell me that I that I just created is an integer. And in fact, you can type of I, and you'll print its type, and you see that you have an int. Now, I can just create a new variable, let's call it f, equals 4.1, and now f is going to be a float. So the type of f is float. Now that you can make integers, you can make floats, you can also make all sorts of other types of variables. So for example, b equals true makes a Boolean variable. Whoa, I can't spell. Variable. And if I say, for example, s equals, I said single quotes can be strings, also double quotes can be strings. So let's say double quotes. This is a string. Shift Enter, we now have a string. So for example, if I print s, I have a string. Now, these are the basic Python types. Now let's look at some more advanced Python types. So I told you how to create a text cell by going to the cell menu and going to cell type and clicking on markdown. Another way that you can do it, if I'm in a cell, I can hit ESC M and it creates a markdown cell. I have to press enter to edit it. So now that we've talked about basic types, let's talk about some advanced Python types. So what are some common advanced Python types? Okay, so most common one is what's called a list. So let's say L is a list. For example, 3, 1, 2, just a list of numbers, integers, floats, strings, anything can be formed into lists. In fact, Python loves lists. So if you can print it, print L, you'll see that we get a list back. So this type here is called a list. Now, you can also have other types which are called dictionaries. Dictionaries, you can think about it kind of like hash tables with keys. So for example, this is a dictionary. We can have, let's say, 2 entries in the dictionary. Maybe foo is, we put foo is the name of the entry, colon 1, so that entry is 1, comma, I'm going to create another entry, say bar, and then let's say that takes value 2.3, so that's a float. And we can take another entry, let's call that S, and that entry is my first dictionary. And now we've created a dictionary with 3 fields with different types. So for example, if you just print D, you'll see the dictionary back that we created. Note that the elements are not in the same order because they're unordered inside the dictionary. I can access an element. So for example, if I print D of foo, you'll see that gets value 1. Dictionaries are extremely useful. So now we talked about lists and dictionaries. One last thing that it's important to note is that Python's no type is called none. So for example, if we say n is equal to, oops, I pressed enter too quickly, sorry about that. If we say n is equal to none, we now have something that has a non-type. So type of n is non-type. So those are the more advanced types in Python. And let's talk about a little bit of ways we can do more advanced printing in Python. And then we're going to go into loops, conditional statements, and defining functions. So let's start with just slightly more advanced printing. So I'm going to press ESC-M and write advanced printing. And so that's what we're doing now. And now, instead of just printing a single variable, I'm going to print a string where you're going to insert some variables in it. So for example, I'm going to print a string, our float value is %s. So that's when I insert, we're going to later on insert the variable f that I defined above in that %s. And we're going to say our int value is %s. And now inserting it, you just put a % at the end of the string, and we're going to insert f and I. So this is what this parenthesis is called, a tuple, inserts f here, this f in the first %s and the I in the second %s. So if I just press enter, you see that our float value was 5.1 and our integer value was 4. And you can do all sorts of more advanced string transformations, which you should go explore on your own because it's extremely fun. And we really benefit from using Python. It's really a simple, easy to prototype, fun programming language. I really love it. So we talked about variable types and we talked about small transformations. So now let's go to the next step. In the next step, we're going to do conditional statements. So ESC-M, I'm going to define another section here, conditional statements in Python. Okay, so there are various ways to build a conditional statement in Python depending on how long and how complicated it is. So let's do a very simple one. So for example, let's say that I want to ask if the integer variable I that I created is equal to 1, that's my test, and the float variable that we created is greater than 4. That's my conditional statement. It's easy to read. And if this is the case, colon, we put a colon after the if statement, we do something. Now in Python, there's no open brackets and closed brackets like you have in C, for example, or in Java. All you have to do is put any amount of spacing or tabulation in the next line, and that's what defines kind of the pieces that will be inside the brackets inside of another programming language. You just keep aligning them the same way. And IPython Notebook is nice because it does all the tabulation automatically for you. So let's say if I is equal to 1 and f is greater than 4, something happened. So I'm going to print the value of I is 1 and f is greater than 4. Now, I'm going to just print that, if this is the case, but I also want to have another condition. I want to have an else condition. And so in Python, you could just type else something, but I want to have multiple conditions, so I want to do another else if some other condition is true. And Python allows you to kind of concatenate else's and ifs together. So if you just create an elif, it's kind of a cute little syntactic sugar here. So if the first condition I is equal to 1, f is greater than 4 does not hold, ask the following question: is I greater than 4? Or, so there's ands, so I put a nice little space here, ands and ors, you just say or. You don't have any kind of that fancy vertical brackets or anything, just say and or. F is greater than 4. Do something else. So our something else is print I is, so let's just print I and f are both greater than 4. Now, if this is not true, we can add another else at the end. So I'm going to backspace in a line in the beginning, just put another else with a colon at the end, and say, if this is not the case, then you say print, say both. So if this condition is not the case, then what we know that I is not greater than 4, and I is not equal to 1, f is not greater than 4. So there's some things that have happened. So we can just say something like both I and f are less than or equal to 4. And we also have that, well, let's say that this is enough. Okay, I'm done. I'm done with my statement. And now remember the values of I and f. I just printed it out here. I was 4 and f was 4.1. So if you go to the first line, you notice that I is not equal to 1. So you go to the next line, you notice that I is not greater than 4. So you go to the next line, you're just going to print this last statement. Both I and f are less than or equal to 4. So if I do shift enter, I execute this conditional, and there you go. I and f are both greater than 4. So that was good. We built our first conditional here. It's all fun. Now that we've done some conditionals, let's do some loops. So again, we're gonna go into the editing mode, markdown, SCM, and we're gonna do some conditional loops. So what kind of conditional loops can we do in Python? So we can do for loops. So for example, you can do a for. So remember we had a list. This is kind of fun. So let me just print it to remind ourselves. So if I print that list L that we built in the beginning, it was 3, 1, 2. So let's do a for loop that iterates over that list. So for, let's say, element in L, for each element in L, I'm going to do something. I'm going to print the element. So this goes element by element of L, and I just call it element. I could call it anything. Let's call it E. So for E in L printed. So it's going to go 3 print, 1 print, 2 print. Let's execute that. And you see 3, 1, 2. And notice that in Python, when you call print, you always insert a new line at the end. So you got 3, 1, 2 in new lines. Now, that is a simple for loop. Lastly, let's create a simple while loop. So you can do fors, you can do while. So for example, while might say, while a counter is, let's just say less than 10, do something. So I'm going to print the counter, and I'm going to add 1 to the counter. So I'm going to say counter plus equals 1. So what this is going to do is create a counter and print it and add 1, print it, add 1 until we get to 10 when it's going to stop. Notice that we never initialize counter, which should give us an error. And so let's just run it and see what happens. We got an error. And whenever you get an error in Python, the error messages sometimes can be a little scary. So you just go here and look at the name of error, and it says down here, name counter is not defined. Remember, we never initialize counter. And it actually goes and tells you a little above what line of the code that error occurred in. So when it first started to test while counter is less than 10, counter was never initialized, it broke. So let's go back and edit. I'm going to insert a new line here. Let's initialize the counter first to any number less than 10. So how about 6? So counter is equal to 6. And I'm just going to execute again. And you'll see now it prints 6, 7, 8, 9. When it gets to 10, stops. In this specialization, we're going to use a number of Python tools that really help us get started with machine learning and build applications that really scale to lots of data. One of them is called S-frames, which is a really scalable data structure for dealing with big tables of data. It doesn't have to fit in memory, it goes into the disk of your computer, and so it can scale up to millions of rows of data, even if you don't have that much memory in your machine. And we'll see lots of examples of that. And that data structured S-frame is part of a package called GraphLab Create that we'll also use in the specialization. So let's see an example of an IPython notebook of how to use the S-frame. So here's an IPython notebook, just so like we did with the previous example, and I'm going to call it Getting Started with S-frames. And just to get a little bit more space on my slide, I'm going to hide that header and hide the toolbar. So now there's a little bit more space in the slide. Now, to get to S-frames, you have to fire up GraphLab Create. And so firing that up is pretty easy. So I'm hitting ESC-M here to get a text box, just like a wiki page. And I'm going to fire up, oops, that I hit enter too quickly. Let me just edit that again. It does not want to let me edit it. There. Fire up GraphLab Create. So every time we want to start GraphLab Create, all we have to do after install it is type import GraphLab. And now we have all the tools of GraphLab Create available for us, including the S-frame and many of the machine learning algorithms that we'll use throughout this course. So the first thing that I'm going to do is load some data from disk. So I'm going to load a tabular data set. So loading a tabular data set as an S-frame is pretty simple. The data set can be in many different formats. What we're going to use is what's called a CSV format in this example, which is just a comma-separated file. And that file is in my current directory. And I actually, if I just call, I'm going to create a variable in S-frame and just call it SF for this example. All I have to do is graphlab.sframe and give it a target, a directory, a file, and it will load it. So in this case, my file is going to be called peopleexample.csv. And here we go. So it prints a few things saying that it parsed and it parsed it correctly. And now we have it. So let's do some S-frame basics. So let's start with some S-frame basics. So some S-frame basics here. If you just type SF, enter, in this case shift enter because we're in the Python notebook, it just shows you the first few lines of that table. So in this case, I'm going to put a comment here. We can view first few lines of the table. So here we go. This is a very simple table. Actually, I'm seeing all the lines. It says the first name Bob, last name Smith, who lives in the United States, has age 24, and we have this for several people. By the way, there's two ways to access the first few lines of the file. You can type SF. You can also type sf.head to show the first few lines. And again, it's a small data set that we're playing with so far, but there's another command called sf.tail that shows the last few lines of the data set, which again, this is a small data set, so first few lines, last few lines, all of the lines. So now that we've taken a quick look at the data set, let me show you something pretty cool. So let's introduce what's called the GraphLab canvas. So this kind of tabular data, graph data, text data, image data that we have, there's many ways you can visualize it. What we have inside GraphLab Create is a data visualization companion that can be used to view the data in various ways. So if you take any data structure that we play with, any data structure in GraphLab Create, so take any data structure in GraphLab Create and you type .show after it. So if you type sf.show, it's going to start the GraphLab canvas and give you visualization, first visualization of that data structure. In this case, we have a very simple data set. When I tap .show, it gives me a link here to a new web page that shows you that data set. So I'm going to decrease the font size a little bit, and you'll see this data set has 4 columns. The first name, Alex, Malcolm, Felix, and so on. The last name, the country this person lives in, and their age. And you see that the max age is 25, the mean age is 22, the median age is 23, the mean age is 23.143, and so on. And if you can click on tabular view, you can actually view the data. And this is pretty cool. If you have a million rows, it's really hard to actually view the data, but this allows you to scroll through millions. 1 billion rows you could scroll through with this tabular view. And now if I click on any column, for example, the age column is going to give me, sorry, I selected something here, which was a little weird. Let me just type reload because I did something funny. A histogram, but if I type categorical, it's going to sort it by the most common value. You see that the most common value is 23. There's 3 of these folks, and so that's 42% of the data has age of 23. So you should play with, we can play with Canvas and visualize the data in various ways and get started. Now, for the notebooks that we're filming here, the Canvas popping up in a new window like this makes it kind of awkward to go back and forth when we're just filming. So instead of opening as a new window, what I'm going to see is how to open the canvas or some of visualizations inside of the Python notebook. So I'm going to call a command called graphlab.canvas.setTarget, and I'm going to say that the target is the IPython notebook, short IPyNB. And we're going to do this again, again, again. But what happens is now the visualizations that we do are all going to target this actual notebook. So let's visualize, again, the age column, but now inside our notebook. So here's what we're going to do. It's pretty cool. We're going to take this S-frame SF, And I'm going to select, square brackets allows you to select a particular column or many columns. So I'm going to select the column age, just one, and I'm going to type dot show on it, and I'm going to tell it that the view that I want is that sorted categorical view that we just saw. So here we go. We just saw that 23 is the most common age. People with 23 years of age, 42% of the data. So now we've seen how to do a little bit of visualization using GraphLab Create. We're going to see several other visualizations within GraphLab and within other tools during the course. So next, we're going to inspect some columns of our data set. So let's inspect some columns of the data set. So let's take a look at it. So if I type SF of country, what it's going to do is select a column country, and since I don't do anything to it, I don't set it equals to anything, it's just going to print it. Now it says United States, Canada, England, USA, Poland, United States, Switzerland. So that's that whole column, but printed horizontally. Now let's look at another column. So for example, let's look at the column age. So sframe.age, I'm just going to look at it. So you have the column is 24, 23, 22, 23, 23, 22, 25. Same one that we did a visualization up here. Now we can take that same column sf.age and do some computations on it. So if you type .mean, it's not saying that column is mean, you mean column, but actually computing the mean of that column, which the mean age is 23, 14, 28, 57, so on. Now you can compute, for example, the max age. So SF of age and say max, and again you get 25. That's the maximum age. Now this is some pretty cool stuff, but let's do more. Let's create new columns in our S-frame. So when you're doing machine learning, often taking columns and transforming them, creating new ones, this is called feature engineering. We're going to do a bunch of those. I'm going to do now a creation of a new column. So let's go back and print our S-frame. And you see that there's a first name column and there's a last name column. There's no full name column. Let's say that you wanted to create a new full name column. It's pretty easy. I'm going to say SF, our S-frame of full name. So there's going to be a column called full name. And what is that column equal to? Well, it's just a concatenation of first name and last name. And in Python, it's really easy to take strings and concatenate them together. All you have to do is put a plus sign. So we can do SF, S-frame of full name is going to be the first name column. So first name. And I'm going to put a space between it. So plus a space plus the last name column. So last name. Now this is pretty cool. I just created a new feature, new column called full name, which is just the first name space last name. It's very easy to do these things in Python, especially if you don't have typos. I see that this is fifth name instead of first name. So, and there we go. So now if you go back and show that S-frame again, you'll see there's a new column called full name that's been placed at the end. So Bob Smith is the first full name there. Now you can do all sorts of interesting things. So for example, you could take the age column, and I'm not going to create a new column, but I'm just going to do add 2 here to the age column, and you see that it's just going to add 2 to every element. And so you can do these kinds of operations. For example, you can do age, and and multiply it by the column h again. Now what happens when you do that? H times h, you're going to get h squared in every element, and you get 566, 529, and so on. So that's how we do various transformations with our data. But these are very simple mathematical operations. Let's do an advanced data transformation. So we're going to use what's called the apply function to do a let's call it an advanced transformation of our data. So this is going to be pretty cool. So we're going to use it to define a new function. We're going to do a bunch of things here. So here's what I'm going to do. We're going to look at the column country. Notice that there's a little bug in my data set. Some people's country is United States, and some people's country is USA, and some people's country is United States. So if you're just building a machine learning model, you'll see that they'll think that USA is a different country from the United States, and you want to make sure that it's the same country. So I'm going to take everywhere where it says USA and substitute that with United States. So we get different counts. So right now, for example, if I do SF of country dot show, so if I just show that, you'll see that United States has 2 counts and USA has 1 count over here. And that's kind of a problematic thing. So let's fix that. So the first thing I'm going to do is create a function that if the input is United States, USA changes to United States. So let's define a function. We talked about how to define a function in Python. I'm going to call it transform country. And it takes into input a country, and you put a column at the end, press enter, and you have to align things vertically. So it says if the country is equal to USA, then we're going to return United States. So this way we normalize the data. Else, so if it's not United States, we don't do anything. So we just return the country as it was. So we created this function transform country. So we can now execute it actually. So let me just show you what happens as an example. So if I compute transform country, give it to input Brazil, it returns Brazil, doesn't do anything. And in fact, if I give it as input Brazil, we say Brazil. And it has with an S, not a Z, also returns Brazil with an S. This is the normalized between the English version of Brazil and the Portuguese version of Brazil. But if you give as input transform country USA, you'll see that it returns United States. So it's going to fix that kind of mistake. Now, what I want to do is go line by line in my data set, and whenever I see the word United States in the country column, I want to change that. So USA in the country column, and change to the United States. So I want to apply this transform country to every row of the data. And you could create a for loop, and that could be kind of annoying. And this is where the apply function comes in. So here's what I'm going to do. I'm going to run a function on the country column. And what apply does, it takes this function transform country that we defined, transform country, and apply it row by row. Let's see what the output would be. So if I run it row by row, it says, it prints some statistics, but it says United States, Canada, England, United States, Poland, United States. So all the USA's changed to United States. And now what I could do is say, I'm going to take my country column, and I'm going to fix it by saying take what it used to be, the country column, and apply this transformation to every single line and just store it back into the country column. And now if you look at our S frame, you'll see that you have United States, no USA in this column. Great. So we've seen how to create functions, how to transform some columns, how to create new columns with S-frames, and how to show our data. Now this tools GraphLab creating an S-frame is what we're going to be using throughout this course, and you will see many ways of applying it and using it, and it's going to make it really easy to build some of the intelligent applications that we're building in this first course.
Okay, so in this module, we're going to talk about regression, which is one of the most widely used statistical tools out there. And the idea is really simple. So we have some set of features, and we want to model how our observations that are associated with these features change as we change the values of the features. And we're going to ground our conversation in a case study of trying to predict house values. So here we can imagine that a house has some set of features like what's the size of the house, how many bedrooms does it have, number of bathrooms, and the list goes on and on. And the observation that we have is what's the value of the house or the house sales price. But the tools of regression go much beyond just thinking about doing prediction tasks. So as we're going to see in the classification course, we can use regression tools for classification. So for example, let's say we have an email and we want to classify whether it's spam or not spam. Well, that email, we can think of having features about the text of the email that's indicative of whether that email's spam or not spam. And in addition, we can think about using regression for analyzing the importance of the features themselves. And we're going to talk more about that in the regression course. Okay, so let's talk about this problem of predicting the value of a house. So this is a very important problem. At least in the United States, it's estimated that household wealth is nearly 50% invested in real estate. So this is clearly important both to consumers, individuals, as well as policymakers. Okay, so I'm here, I want to sell my house. I have this nice big lime green house. But I don't know how much to list it for. So I'm not sure what value my house has. And so how do I think about estimating the value of the house? Well, it might make sense that what I do is I look at other recent sales that have occurred in my neighborhood. So I look locally at the region around me and I say, how much have the other houses sold for and what do those houses look like? So what I'm going to do is I'm going to record for each one of these recent sales, what was the sales price and also what was the size of the house that was sold. I'm going to say that that's what signifies whether that house is similar to mine or not. Okay, so being a statistician, I'm going to take all these observations I had and I'm going to make a plot of them. So in the US, at least, the size of the house is measured in the by square feet. So that's going to be my x-axis. And then my y-axis is going to be the sales price of the house. Okay, so that's my y variable. And each one of these points represents some individual house sale. So here, this is one previous house sale in my neighborhood. And just to introduce a little bit of terminology here, when we're talking about regression, people often refer to x, this variable x, as being the feature. That's the terminology we've been using. People also talk about it being the covariate or the predictor. And in some cases, it's called the independent variable. And then our observation y is, as I just said, I tend to refer to it as an observation. People also call it a response or the dependent variable. Okay, so the question is, how am I going to use these observations to estimate my house value? Well, I might look at how big my house is and look for other sales of houses of that size. Well, most likely there are going to be exactly 0 house sales of other houses that had exactly the same square footage as my house. Okay, so I say, well, I can't use this approach. I'm going to be a little bit more flexible and I'm going to look at some neighborhood, not geographic neighborhood, some little range of square footage around my actual square footage here. So I'm going to say, okay, let's look at all house sales that were for houses within this range of square footage. But even with that approach, in this case, for example, I only have 2 house sales that I'm going to base my estimate off of. So I don't really feel very comfortable with that. And what I'm actually doing here is I'm throwing out all these other observations as if they had nothing to do with the value of my house. And the question is that reasonable? Do we actually believe that there's actually no information in these other observations? Well, when I look at this data and when I think about data, I like to leverage all the information that I can to come up with good predictions. Okay, well, instead of the analysis that we just did, we can instead think about modeling the relationship between the square footage of the house and the house sales price. And to do this, we're going to use something that's called linear regression. Okay, so to leverage all the observations that we've collected, what we want to do is be able to understand the relationship between the square foot of the house and the house sales price. And so the simplest model we can use for this is just fitting a line through the data. So here's an example of a line fit to this data. And this line is defined by an intercept, W0, and a slope, W1. And so often we'll talk about W1 being the weight on the feature X, or it's called the regression coefficient. And what this weight has an interpretation of is as we vary X, the square footage of the house, how much of an impact does that have on changes in the observed house sales price? Okay, so these two things, our intercept and our slope, are the parameters of our model. And so to be very explicit here, we're going to write this function, this linear function here, with a subscript w that indicates that this function is specified by parameters w, being the set of W0 and W1. Okay, so this is the line that we fit through the data, but a question is, which line is this, the right line or a good line to use for a given data set? So maybe we could draw this line or this one instead, and each one of those is given by a different set of parameters W. And the question is, which W do we want to choose for our model? Okay, well, to think about this, let's talk about defining a cost for a given line. And one very common cost associated with a specific fit to the data is something called the residual sum of squares. So the residual sum of squares, we take our fitted line and we look at each of our observations and we look at how far is that observation from what the model would predict, which is just the point on the line. So we look at all of these distances here, and we actually look at the square of these distances. That's why it's called the residual. The residual is the difference of your prediction and your actual observation. And we're going to look at the square and we're going to sum over them. Okay, so this is the equation here more explicitly, where we have the price. This is our observed house sales price for the first house. And what is this term here? So if this is what I'm calling dollar house 1, then what this point here is if this is square footage of house 1, then this X that I've drawn here represents exactly this term here. This is that value, the point on the line. So this dollar sign minus this term here is the difference between our observed house price versus what our model, just this line, predicts for this given house square foot. And we're squaring that, and then we're summing over all the different houses in our data set. Okay, so when we think about trying to find the best line according to this metric that I've defined here, this residual sum of squares, what we do is we search over all possible W0 and W1, so all possible lines, and we choose the one that minimizes this residual sum of squares. So we're going to denote the resulting W as W hat. hat. So remember, that's going to be the set of w hat 0 and w hat 1, our intercept and our slope. Okay, so there exists really nice and efficient algorithms for computing this w hat, this search over all possible w's we could look at, parameters of this model. But we're going to discuss these algorithms more in the regression course. Okay, so now let's talk about how to take our estimated model parameters and use them to predict the value of my house. So I've gone through, sorry, this star shouldn't be there. This should be a hat, just to be clear. And I've gone through and plotted the line associated with our estimated w0 hat and w1 hat. And now here's my house. This is its square footage. And the best guess of my house price is simply what the line predicts. So I go and I compute what is the value for this square footage of my house, which is w0 hat plus w1 hat times the square footage of my house. Okay, very, very straightforward. Okay, so up to this point, we've just considered fitting the data with a line. And the question is, was that a good choice? So I'm actually feeling pretty good about my analysis, to be pretty truthful here. I fit this line, I minimized the residual sum of squares, I made a prediction for my house value, and in doing so, I leveraged all of these observations that I went through and recorded of all the recent house sales. And I go to Carlos and I say, hey, look at my analysis. This is my estimate of the value of our house. And he goes, well, I'm not so sure, because really to me, I'm not sure that this is a linear trend. He actually says it's not linear. Or according to my cartoon, he says, dude, that's not a linear relationship. Dude. No, I guess Carlos would not say dude, but anyway. Bro. He says bro, okay. Bro. He always refers to me as bro, of course. Okay, but anyway, the point is, Carlos doesn't think that it's a linear relationship. He thinks, maybe it's quadratic. He said, did you try a quadratic fit? I go, well, no. I look at the plot that he just put up here, and I say, actually, that looks pretty good. And what do I have to do? I have to figure out which is the best quadratic fit to this data. And how am I going to do that? Well, I'm going to go again and I'm going to minimize my residual sum of squares. So I'm just about to go minimize my residual sum of squares. So let's talk about what that would involve. Because when I'm looking at a quadratic function, I now have 3 parameters here. I have my intercept, which is just where is this curve? Up and down on the y-axis, and then I have this linear term of x, and then I also have this extra term here, which is now the square of x. That's where I get that quadratic component. But I want to make one quick comment here, so a little aside, that this is actually still called linear regression, and the reason is because we think of x squared just as another feature. And what we see is that the w's always appear just as w's, not w squared or other functions of w. And we're going to discuss this in more detail in the regression course. But remember, even though we're talking about a quadratic function fit to the data, this is still called linear regression. Okay, but the point I want to make here is we have 3 parameters. So when I'm going to minimize my residual sum of squares, I have to search over the space of 3 different things now. I have to minimize over the combination of best w0, w1, and w2 in finding the quadratic fit that minimizes my residual sum of squares. Okay, so I'm just about to go and do this computation, which actually turns out to also be efficient. And again, we're going to discuss the generality of that in the regression course. But then Carlos has a brilliant idea. He says, wait. I told you about that quadratic, but did you try a 13th order polynomial? And I go, no, I didn't.
Makes sense.
It does. It makes a lot of sense. Look at this. This is pretty good. This is the fit that Carlos gets with his 13th order polynomial. He says, I just minimize your residual sum of squares. Pretty good, right? My residual sum of squares here are basically 0. But I'm personally not feeling so great about this because I'm looking and I'm saying, my house isn't worth so little. I know that. I do. Yes, we talked about residual sum of squares as being this cost of the fit. And yes, Carlos seems to have really minimized my residual sum of squares, but something's not sitting right with me. This function just looks crazy. So for each model order that we might consider, for example, a linear model, or we also talked about using a quadratic model, all the way up to our very crazy 13th order polynomial. And of course, we could consider even higher order models. Well, what happens to test error? Sorry, I don't mean test error. Let's start with training error. A lot easier to think about. So training error. As we increase the model order, well, that model is able to better and better fit the observations in that training data set. So what we're going to have is we're going to have that our training error decreases with increasing model order. So remember the curves that we had the residual sum of squares associated with that linear fit, quadratic fit, all the way up to the 13th order polynomial that basically hit each one of those observations. So we saw that our residual sum of squares was going down and down and down. So that's true even if we hold out some observations and just look at our training data set. So we're going to have our training error decreasing and decreasing as we increase the flexibility of the model. But okay, so let's just annotate this as being our training error, particularly for our estimated model parameters, W hat. So let's be clear about what we mean by W hat. So for every model complexity, such as linear model, quadratic model, and so on, what we're going to do is we're going to optimize and find the parameters W hat for the linear model. We're searching over all possible lines, minimizing the training error. Remember, that's what we said a couple slides ago. We said that the way we estimate our model is we're going to minimize the error on that observations in our training data set. So that's how we get W hat for the linear model, and we compute the training error associated with that W hat. Then we look at all possible quadratic fits, minimize the training error for over all the quadratic fits. That's how we get W hat for the quadratic model. And then we plot the training error associated with the W hat for the quadratic model, and so on. Okay, well, we can also talk about test error, but here it's a little bit more complicated because what do we think is going to happen as we increase and increase our model order? Well, what we saw, if you remember that 13th order polynomial fit, that really crazy wiggly line, we had really bad predictions. So when we think about holding out our test data, fitting a 13th order polynomial just on the training data, we're going to get some wiggly crazy fit. And then when we look at those test observations, those houses that we held out, we're probably going to have very poor predictions of those actual values. Okay, so what we're going to expect is that at some point, our test error is likely to increase. Okay, so the curves for test error tend to look something like the following, where maybe the error is going down for some period of time, but after a point, the error starts to increase again. Okay, so here, this curve is our training, not our training, our test. Oops. Our test error for these fitted models where the models were fit using the training data. Okay, so these are what curves tend to look like for training error and test error as a function of model complexity, and how we think about using these ideas to actually select the model or the complexity of the model that we should use for making our predictions, we're going to discuss in a lot more detail in the regression and classification courses. Okay, so far we've assumed that the only feature relevant to the value of my house is the square feet of the house. But I dig into the data set a little bit more, and I look at a house that's supposed to be very similar to mine. It's a house that has very similar square footage. And so this house is definitely making an influence on what the predictions are for my house. But I look at it and I look at the specific listing, and it shows that that house only had one bathroom. It's actually quite a big house, only one bathroom. And I say that's really, really not comparable to my house, which has 3 bathrooms. So that the value of that house sales price, really shouldn't be indicative of what my house sales price should be. So instead, what we can think about doing is adding more features. So instead of just looking at the relationship between square feet and price, we can add number of bathrooms. And now for each one of the listings that I looked at before, I'm going to have to go through and record how many square feet that house had and the number of bathrooms. And I'm going to plot each of these points in this 3D space. Okay, so it's this hypercube of square feet versus bathrooms versus price. And now instead of fitting a line to the data, if I'm thinking about just a very simple model, I can think about fitting a hyperplane. Okay, so it's just a slice through this space. Where here, this is the equation of the hyperplane, and this is the equation of this plane. So we have W0, which is our intercept, just where this plane lives up and down on the y-axis. And we have W1 times the number of square feet and W2 times the number of bathrooms. But the question is, where do we stop? Do we just want to include the number of bathrooms as our additional feature? There are lots of things we could think about including. We could think about, in addition to our square feet, number of bathrooms, there's the number of bedrooms, the lot size, how old the house is, and the list goes on in terms of different properties of the house that could be influential in assessing its value. But we're going to actually hold off on this question of looking at which features are important for this regression task until we get to the regression course. So go to the regression course to learn more about this topic. Okay, well, we've talked quite extensively about using regression for the task of predicting a house value, but of course the number of applications in which regression can be used are quite large. Let's discuss just a few examples. So one is for predicting your salary after you take this machine learning specialization. So you work really, really hard in this specialization, and hopefully after that you can go earn a really cool job, have a very big salary. But to predict how much your salary will be, maybe that depends on things like what was your performance in the various courses of the specialization, what was the quality of your capstone project, how many forum responses did you make, and so on. Okay, when we think about predicting your salary, y hat, what we're going to do is we're going to estimate our model parameters, W0, W1, W2, and W3, which are our intercept and our weights on your performance in the class, the quality of your capstone, and your participation in the forum. And when we're estimating these model parameters, what we're going to use these features for other students who have taken this course and the observations of what their salaries were and the jobs they got after taking this machine learning specialization. Another application of regression is for doing stock prediction. So here we might think about the fact that the prediction for the price of a stock tomorrow depends on the recent history of the stock price. It depends on news events, different things going on in the world, as well as the value of other related commodities. And a very different application than thinking about predicting stock prices or your salary after this specialization is you're sitting on Twitter, you tweet something, and you want to know how many people are going to eventually retweet what you just tweeted. Well, this might depend on how many followers you have, how many followers your followers have, different features of the text of what you tweeted, the popularity of the hashtag you included, number of past retweets of your tweets that you've had, and things like this. And it turns out these types of models can actually be really good at predicting the eventual number of retweets of your tweet. And another very different application is maybe you have a smart house. There's lots of different sensors in this house and lots of different things you can control, like temperature settings in different locations. vents, window blinds, and things like this. And you have a home office and you have a desk, and you want to be able to predict what's the temperature at your desk based on various settings of all these controls. But there's actually no sensor directly at your desk. So what you can think about doing is fitting a spatial model in order to predict what the temperature is at all these different locations throughout the house. And this might depend on features such as the thermostat settings in the house, whether the blinds are open or closed, temperature outside, how you've set different vents, and as well as things like the time of the day. Okay, so hopefully you see that applications of regression, and this really just touches the tip of the iceberg of where regression is used, but it's really quite a powerful tool. In this module, we've seen how regression can be used to predict house prices and also be useful in a wide range of other applications. So in the introduction to this course, Carlos introduced this machine learning pipeline where we go from data, which gets shoved into some machine learning method, and we use that to derive intelligence. Well, let's dig into this block diagram and expand it now that we've seen some of these machine learning tools in a little bit more detail. Okay, so now we know that what we actually use to fit our data is some training data set. So that's going to be our data. And in our housing application, where we're going to predict the price of some house, the data that we collected was we had this table of the house ID and some set of house attributes, as well as that house, the house's sales price. And we had this for a whole bunch of houses in our neighborhood, and we collected this data into some table. So that represented our training data set. And then we took that data, and what we did was shoved it through some feature extractor, which in this case is a very simple feature extractor, where we just choose some subset of the house attributes. So in the examples we looked at, X, our set of features, represented things like we looked at square feet of the house, and we also looked at number of bathrooms, and we talked about possibly using more features. Again, we'll talk about that more in the regression course, but those were two that we examined in this module. And so then what did we do with these features? Well, our goal was to take these features and have some type of model that led to a prediction of the house price. Okay, so our output, the intelligence that we're deriving, is the predicted house price. And we're going to do this for every house in our training data set. We're going to take its associated features and shove it through this machine learning model and predict the house price. And what's the machine learning model we talked about? Well, in this case, it's regression. That's our specific machine learning model that we're looking at here. Okay, but remember that this machine learning model had some set of parameters. Okay, so the parameters we call W, these are the weights on our features. So for example, it's the weight on square feet or number of bathrooms and so on. More technically, these are called regression coefficients. And we talked about estimating these parameters from data. So that's our W hat is our estimate of these parameters. And how did we talk about doing that? Well, we took our predicted output, so our predicted house price, and we compared it to the true house price. So the actual sales price that we recorded in our training data table. So Y here is our actual sales price for the houses in our training data, and we compare to the predicted house price, and we use a quality metric to measure how well we're doing with our prediction, using our model, using W hat as the parameters of that model. Well, how well are we doing? What was the error metric we talked about? The error metric we talked about was something called residual sum of squares, where we just sum up the square difference between the actual house sales price and the predicted house sales price, summing over all houses in our training data set. Okay, so our quality metric is going to take our predictions and our actual house sales observations, spit out this error, and it's going to go into a machine learning algorithm that's going to be used to update the weights, update our parameters of our model. And we're going to talk about this machine learning algorithm or different variants of it a lot more in the actual course on regression. But this is the overall flow chart for this machine learning method for our house prediction problem. And this loop here, where we're taking our predictions, computing our error relative to the actual house sales prices, and updating the weights or our model parameters, this process tends to happen in an iterative way where we update values again and again. Okay, so if we abstract away, what we see is we have some training data set, we have some feature extraction process, we have some machine learning model, and it's going to produce some intelligence, which in this case is a prediction, and we're going to assess the quality of our intelligence with some quality measure, and we're going to use that error or accuracy, depending which way we're thinking about measuring it, to adjust our model parameters using some algorithm. And we're going to see this type of flow for machine learning again and again. In this module, we've seen how to take our data and derive intelligence using something called regression, where we have a model that relates our features to our output. And we talked about this in the context of predicting house values. And you also work through a really interesting IPython notebook. And from this, you should be able to deploy really interesting regression models in practice now.
In this module, we talked about how to do regression. In fact, we talked about how to use it to predict house prices. Now we're going to build together an IPython notebook using Python to predict house prices for a real data set based on what's called King County data. King County is the county or the region where the city of Seattle, where Emily and I live, is located. So we're going to take some of that data, it's public record data, and actually build together a regression notebook to predict house prices. So let's get started. Okay, so here's a blank IPython notebook. And just to start, what I'm going to do is hide first let's change the title. So we're going to change the title to Predicting House Prices. So we just renamed it. And I like to go to the View menu and hide the header and hide the toolbar, this part at the bottom, so we have more space on the slide. So we've done the hiding. And the first thing we're going to do is fire up GraphLab Create, the tool that we're going to use to run some machine learning algorithms in Python. So I'm going to type scam, and we're going to say fire up GraphLab Create. So we do that by typing import GraphLab. And that just starts up GraphLab Create. Now, our task today is to predict house prices. So the first thing that we're going to do is to load some house sales data. So this is public data, public record of houses that got sold in the Seattle region. So I'm going to call this table data sales, and I'm going to say graphlab.sFrame. Remember we talked about sFrame as the data structure for representing tabular data in GraphLab Create. So it's a really fast, out-of-core data structure, and we're going to load up some house listings in there. So this is going to be called home_data. And notice that IPython Notebook does autocomplete for you. So that just happened there. And so if I just type, this is loading it up and it's firing up GraphLab Create. If I just type sales here, you'll see what that data looks like. So I'm going to scroll up a little bit to the top. I just type sales and it says there was an ID for a date for the sale, the price, number of bedrooms, number of bathrooms, square feet, which is kind of like the American version of square meters if you're living in other countries, for the house, square feet for the lot of land, number of floors, and a bunch of the other categories, whether the house has a view or not, whether it sits on a grade, which means it's on a hill, and a bunch of other measurements. So we've loaded this house data, and it looks pretty cool. The first thing that we're going to do is use GraphLab Canvas to do a little bit of visualization. So what I'm going to do is, again, create a cell, and this says exploring the data for housing. So housing sales. So we're going to do some data exploration. So we're going to take the sales data, and I'm going to show. So when I type .show, it's going to show some visualization of that data. And in particular, what I'm going to do is view, just rather than letting GraphLab create this default view, we're going to just do a scatter plot. So we'll see what a scatter plot is in a second, but just type view scatter plot that relates two variables. On the x-axis, we're going to have the square feet of living space, and in the y-axis, we're going to put the price. So what that should show us is the relationship between square feet of living space and price. Now, one little trick that I like to do when I create notebooks is that sometimes we push out GraphLab Canvas in a new tab, but often it's kind of fun to just plot those scatter plots and simpler plots inside the notebook itself. So I can print it out and hand it off to somebody. So the way to do that is I can just tell GraphLab Canvas to set its target not to be the browser, which is the default target, but to be the IPython notebook. I just type canvas.setTarget IPyNB, IPython notebook, and it's going to plot this scatter plot on the notebook itself. So if I hit enter here, what's going to do is take those two axes and just plot them together. So here we go. On the x-axis is the square feet of the house, and the y-axis is the price. So let's kind of browse this a little bit. So for example, more square feet are big houses. So if I mouse over here, you'll see that this big house had 5,990 square feet, which is pretty big. That's like 600 square meters. And it was sold for $2.2 million, which is quite a lot of money. Now, you also notice there's a nice relationship that bigger houses tend to cost more. There's a big blob of houses here, so most houses are between 1,000 and 3,000 square feet. And even at this level, say this house over here, it's an outlier. So even though it's only 1,910 square feet, it was sold for $1.5 million. While down here, there's a house that is similar, 1,700 square feet, that's sold for just $149,000. So it's a big discrepancy. And here's the biggest outlier of this data set. This house has 3,730 square feet and got sold for $2.5 million. So we've now built a simple scatter plot, and we get an idea of what our data looks like. And the question is, can we use the scatter plot to predict sales price from square feet of living? So we're going to do a simple regression model. So let's do that. I'm going to hit askm, and we're going to say create a simple regression model of square foot of living to price. All right, so let's do just that. So remember from the lectures that the first thing that you do before you do anything to your data is to split it into a training set and a test set, because you never want to do training or learning on the test data. You want to do that just on the training data. So let's do that, split. So I'm going to take my data and split it into training data and test data by calling a function that's called, that you can apply to an S-frame. So it's called the random split function, sales.randomSplit. By the way, what I did there was just use tab complete. So let me just show you that little trick just for a second. So if I just do sales.r and I press tab, you'll see there's a few things I could do: random split, read a CSV file, remove columns, rename columns, and so on. So I'm going to just do random split. And what I'm going to tell it is to do a 0.8 split. So 0.8 of the data, 80% is going to be for training and 20% is going to be for testing. Now, one last thing that will be useful for your homeworks and in general to make sure that you have always the same results is to set a seed for the split. Because it's a random split, it's a pseudo random number generator, we can set a seed to it. And I'm just going to set the seed to be any number we want. For example, it could be 2015, it could be many things. So I'm just going to set it to 0. So now every time I do this random split, it'll split the data in the same way. So now we have some training data and some test data. And what we can do next is build, so I'm going to do as a subheader here, build the regression model. So GraphLab Create has many algorithms pre-implemented for various machine learning tasks, or you can implement your own if you like. And during the sequence of the specialization, you're going to write many algorithms of your own. But for this course, we're just going to use pre-implemented algorithms so you can really try to understand how machine learning works. So what you can do with machine learning. So what we're going to do is build a square foot prediction model, just call it square foot model. And in GraphLab, there's something called linear regression. So linear regression is what we learned, what we explored and talked about and really understood quite well during the module that Emily was teaching. And so if you just say linear regression.create, it's going to create a linear regression model for you. And .create is the name of the project here, GraphLab Create, and create is also the verb that you use to create various things with GraphLab Create. So we're now going to create a linear regression model, and what do I have to give it as input? I give it the training data. So here's the training data. You have to say what variable you're trying to predict. So that's the target. So I'm going to say the target is going to be price. So I'm trying to predict price. And the question is, what are the features? What is the input? So I'm going to say that the features, and by the way, you can use tab complete even within parameters of functions, which is pretty cool. So the features is a list of features. If you don't give it anything, it will use all features, all columns of the data. But here, the only feature input we want to use is a square feet of living space. And that is a string that I need to put in. So I forgot to put it in quotes. So let me fix that real quick here. So open quotes, close quotes. All right, very good. So let me just reread that for us. So square feet model, GraphLab, linear regression.create on the training data to predict the target price using features square foot of living. And let's go and execute this. Oh, training data, I wrote data twice here. you see the error came out here, training data underscore data. So now let's execute. So what's happening here? It's done actually, but what we did was create a linear regression model. It used a particular algorithm called Newton's method, but GraphLab Create chooses an algorithm automatically for you unless you tell it which one to use. And this algorithm allows you to make some predictions on the data. And so let's actually use a model. So next, we've now trained a linear regression model. Let's evaluate it. So what we're going to do next is evaluate the simple model. So how to evaluate it? We're going to look at the test data. So remember, we had split test data. Let's understand test data a little bit. So for example, let's print for the test data for the price column, what's the average price? What's the mean price? So this just computes the average price, and the average price for the test data, or for this data from Seattle, is $543,000. This is how the average house costs. It's pretty expensive, actually. Now, we've built a square foot model, and so what we want to do is evaluate it on this test data. So we're going to take the square foot model that we built, and we're going to call what's called the evaluate function, which can take a test data set and print out or return some statistics of how well that fit is doing. So let's do that. So I'm actually going to type print in the beginning because it formats it a little bit nicer, and you'll see that the maximum error over all test houses was 4.1 million. So there was one house that was an outlier. It was really badly predicted. And the average error, so the RMSE, so the root mean squared error, we talked about this. Emily talked about this with us during the lectures, is $255,000. So that's the RMSE. So we built this simple model. We tested it. It's pretty high RMSE. But let's look at some predictions it tries to make from the data. So what we're going to do next is let's show what our predictions look like. Now, I talked about using GraphLab Canvas as a way to visualize the data, but you can also use other tools out there to visualize, other Python tools. So just as a simple demonstration of that, I'm going to import one such tool. It's a pretty commonly used one. It's called matplotlib. And from there, I'm going to import something called pyplot, which allows you to do some plotting in Python. And I'm going to refer to it as PLT. So when you do an import in Python, if you type import matplotlib.pyplot as a particular piece of the package, and I write as PLT, now I don't have to write this whole thing, matplotlib.pyplot, blah, blah, I just write PLT. That's why we use the as command. So I'm going to import it. And one little trick I'm going to do, just like you did with Canvas to make sure it prints inside the notebook, I'm going to do it here too. So you put this percent and you say matplotlib inline. So that just plots it on the notebook itself. So let's hit enter. We've imported it. And now I'm going to actually build a matplotlib plot for for the results here, for the regression results. So we're going to plot plt.plot, and there's a function here. And I'm going to plot my test data in two ways. So it's interesting. You can plot two multiple plots on top of each other with matplotlib, and we're just going to do that together. So I'm going to take my test data, and in my test data, I'm going to plot on the x-axis the square feet of living space, and in the y-axis, for my test data, I'm going to plot the price. So this is kind of similar to the plot we did above, the scatter plot. And I'm going to refer to each one of these points as test points. I'm going to draw them as a dot. So that's what this little dot here does. However, I'm also going to plot one more thing. So I'm going to plot two things on the same plot. Actually, so I'm missing a comma out here. So in addition to plotting the test data, let's plot our predictions. So again, on the x-axis is going to be the square feet of living space. But on the y-axis, I'm going to plot something else. I'm going to plot what my model predicted for each one of those houses. So remember, we built a square foot model, and it has many functions associated with it. If you go down, one of those functions it has is called a predict function. And the predict function, you can give it a bunch of data as input, and it's going to output an S array, so a column of data with the predictions for each one of these input elements. So I'm giving it the test data, and I'm going to draw it as a dash. Now, before I execute this line, just take a moment to imagine what this plot is going to look like. So the top line says, plot living space for the price of test data with dots. It's going to look very similar to the scatter plot that we drew before. And the second line says, plot the input houses living with the prediction with a dash. And now remember, this was a simple linear regression model with a single variable, so all we have is a single variable. And as we covered in the lectures, we're just going to plot a single line. And we'll see that execute, and here we are. So the blue dots here are the test data for the houses, while the green line corresponds to the predicted house values. And in fact, we can actually look at the coefficients of that line from a model. So we can take this square foot model that we build, and we can call the function get, and we can get the coefficients. So these are what in the course we call the weights. And so there are two weights, two coefficients. The first one is the intercept, so where this line crosses the y-axis, in this case, minus $44,000. And the second one is the coefficient of the square feet, so this angle, which corresponds to, if you interpret it in this case, the price per square feet. How much does a square foot of a house cost? If I had another square foot, how much it adds? And it's $280 per square foot. This is the kind of average for Seattle. Some houses cost more per square foot, the ones up here. Some houses cost less, but on average, if you think about it, it's about $280 per square foot, or at least according to this regression model. We've done now some simple regressions, of our data just using square foot of living. But if you remember, our data set had many other columns associated with it, or features. So what we're going to do next is explore other features in the data. So let's do some exploration of other possible features we might use. So I'm going to use a set of features. So let's create a list of the features I'm going to explore. We call it features. And these features are going to be the number of bedrooms, the number of bathrooms, let's see what else, the square foot of living space, which is what we've been exploring so far. In addition to this, I'm going to include the square foot of the lot. So this is how much land the house has all around it. The number of floors in the house. And finally, I'm going to include a variable called the zip code. And so the zip code is, the zip code in the United States is what other countries call the postal code. In Brazil, we call it CEP. But there are many names in different places. That's what we'll include. So let's say if I take the sales data and I just select these columns, I just select the features column here. Why don't we call them, just to be totally clear, instead of calling them features, I'm going to call them my features. Shift enter, and then I'm going to look at what my features columns look like. So I'm going to type .show. Remember, you can type .show anything with GraphLab Create on the S frame for sales, selecting the my features. And now we're going to have a visualization of these features. So let me just walk you through this visualization. Get my mouse here. So bedrooms. Let's look at frequency. There are 13 different unique types. In fact, there's some houses with 10 bedrooms. There is, most houses have 3 bedrooms. Some have 4, some have 2, some have 5, and very few have more. With bathrooms, it turns out that housing in the US can have fractional number of bathrooms. When you say, for example, 2.5 bathrooms is the most common number, is because if you have a house with a bathroom with a bath in it, it's called a full bath, it counts for 1. But if you have just a bathroom that has a sink and a toilet in it, it's worth 0.5. And so here you have 2.5. In fact, if you have a bathroom with a sink, a toilet, and a shower but no tub, that's worth 0.75 in the US. So there you go. That's why you can have one bathroom is the second most common, and then you have this 1.75 bathrooms, which is probably going to be one bathroom, one full bathroom for bath, and one bathroom for shower. And you can see the distribution here. Similarly for other things like square foot of living, and the number of floors. Most houses have 1 floor, some have 2, and then the zip code. The most common zip code is 98103, which is an area where a lot of people live in Seattle. Okay, so we've seen a high-level visualization of the different columns of the data. Now let's look at some other relationship to the data. Let's do some fun visualization here. So I'm going to take the sales table and I'm going to type show. But the view that we're going to do is not going to be a scatter plot, but it's going to be what's called a box whisker plot. And this box whisker plot is going to relate 2 variables that we looked at. On the X side, I'm going to use the zip code. So this is the postal code that we discussed. And on the Y-axis, I'm going to plot the price. So what we're going to see is the relationship between the location, the zip code, where the house is, and the price. And we're going to see that with what's called a box whisker plot. So I'm going to press Shift Enter, and we're going to plot it. And here's what we'll see. So you'll see, for example, this area's zip code, postcode 98003 has a significant lower price. So average price is low, that's the red line, and not a lot of variability. While this other zip code 98004, so this is 003, 98004, has a highest average price, much higher, 1.something million, 1.1 million, and a huge variability. So the houses range from something like what is this? $800,000 to almost $4 million. But here I'm just showing a few zip codes. If I drag down here, you'll see more and more zip codes. And wow, what is this one over here? There's one that's astronomical. It goes out of the scale. Some houses here cost like, what is this? $7 million or something. And this postcode is 98039. Remember 98039? We'll come back to it at the end of this notebook. It's kind of fun. We've built a simple model just relating square feet of living space to the price of houses. And then we explore some other features like zip code. It's clear the zip code makes a big difference. And there's other features, bedrooms also make a big difference. The question is, can we get a better model by including more features, more of these? And so let's look at that. So what we're going to do here is build a regression model with more features. So this is using this bigger feature set that we just described. So the first one I called the square feet model. Let's call this the my features model. So the my features model is again going to take graphlab.linear-regression.create. So we're going to create it. I'm going to use the training data just like we did before. Our target is again going to be the price, just like before. However, the features here that I'm going to use are going to be those features, what I call my features, which I created earlier. So let's go and execute this. So now I use more features and it's training and I think it's done. It's done. Using those, I forget how many, 8 features. I use this, let's just print them out here. Print my features. So I use bedrooms, bathrooms, square foot of living, square foot of lot, floors, and zip code. Now, we have 2 models. We have the square foot model and we have my features model. How do they compare in terms of performance? So here's what I'm going to do. I'm going to print the square foot model dot evaluate on my test data. And I'm also going to print the my features model dot evaluate on the same test data. And let's compare, let's see what happened. Okay, so to start with, we saw that the biggest error in the simple square foot model was $4 million. Now it's down to $3.4 million, 3.49, so 3.5 million. So it went down a bit. And root mean squared error, kind of the average error, went down from $255,000, as we had over here, to $179,000. Now, if you add more and more features, your error is likely going to decrease quite a bit more because there's quite a bit of data here and there's lots that you can learn. But again, just adding some extra features already helped us with our performance. We've learned, now together we learned 2 regression models from our data. One just based on square foot of living, the other one based on these more advanced features. So let's apply these models. Let's see what it looks like when we use them in practice to predict house prices. So what we're going to do is apply these learned models to predict prices of 3 houses from the data set. So 3 different houses. So the first house is, and this is 3 that I picked that had kind of different sizes, different properties. They look a bit different in different neighborhoods. So let's just look at them. So the first house is from our data, and so what we're gonna do with this house is, so this is from not data but sales data. So out of my sales data, I'm going to select the house whose ID is equal to a particular ID. And so the county record gives this string IDs for every house. It gives it a number. So this one is 5309. I'm copying from a piece of paper here. 101 200. So a particular house for a particular ID. And so I'm selecting it. And if I type house 1, you'll see what it is. So it's the house that has this particular ID. It got sold on this date for $620,000. Had 4 bedrooms, 2.25 bathrooms, 2,400 square feet of living space, and so on. Now, what you can do is, in IPython Notebook, you can embed not only markups and text and Python code, but you can also embed HTML and images. So let me just do that for you right now, just as an example. So I'm typing XM, and I'm going to add an image to my notebook. And this image is an image that I downloaded from the county records for this particular house. So the image is on my directory. It's called house. So house 53, what was the number? 09 101 200. So this is going to be pretty cool. I'm going to see a picture of the house we're trying to make a prediction for. Oops, I must have typed that wrong. Oh yeah, I forgot. It's .jpeg. And that's pretty cool. Here's a picture of the house we're pricing. So this house was sold in 2014 for $620,000. It has 4 bedrooms, 2.25 bathrooms, and it was built, for example, in 1929. Now let's see what our model predicts. So we had 2 models. So we had first, so the true price of the house. Let me just print that to remind ourselves. So this is house 1 of price. This is 200. So if I just type print here, it'll look a little nicer. $620,000. This is the house price. Then let's see what my first model predicts. So that was the simple square foot model that we built. When you give it, so I'm going to type .predict to predict the price of house 1. And it says it predicts it as $628,000. So pretty close, actually. That's really good. And let's see what adding more features did for us. My features model dot predict house 1. So you remember, on average, the my features model, with adding more features, give you better performance. Now, if you look at the prediction here, it's $720,000. So the square foot model had a better prediction than the one with more features. So what we learn here is, even though on average, adding more features give a better prediction, for this one particular house, the simple model did a better job than the more advanced model. But this is to be expected. Not always, but sometimes it's going to do better, sometimes it's going to work, but on average, it's going to do better. So we've seen this one example, and now let's look at a second house. So I'm going to now prediction for a second fancier house. So let's look at that. So let's call this house 2. So house 2 from our sales data, is going to be the one, again, we're going to use a filter here. So it's the one whose ID is equal to 1925069082. So let's take a look at what house 2 looks like. House 2 was sold in 2015 for $2.2 million. It has 5 bedrooms, 4.25 bathrooms, so many more bathrooms, 4,640 square feet of living space, so it's much bigger. It's about 460 square meters. It's a pretty big house. So let's look at an image. I kind of downloaded also an image for this house. So here's my little cheat sheet for the image. And I'm going to insert it. So let's scan. So as before, we're going to do an image whose source. So this is I downloaded to the basic directory here. It's called house 1925069082.jpg. Close, not jog, but JPEG. So that should work. So remember that other house cost $620,000. This one costs $2.2 million. Let's take a look at it. It looks fancier, it looks cool, it has a bigger yard, but check this out. It's on the water. It's a waterfront house. You know, that explains why it costs $2 million. It's fancier, much fancier. So let's see now what our models predict for the value of this property. So it costs $2.2 million. Let's print what the square foot model predicts. So just like before, we're going to do dot predict on house 2. And it predicts it costs only $1.25 million. So it didn't do so well. So let's look at what the more advanced model, so my features model, dot predict does. And before I hit enter here, it's good to start thinking about what should happen here. The other house, the one above, where the one with more features, model with more features didn't make a big difference or actually did worse, was a pretty standard house for Seattle. Standard number of bedrooms, standard number of bathrooms. It was kind of common, so you expected both models to do about the same. But this house is crazy. It has features which are hard to capture just because of the square feet. It has waterfront, it has lots of bathrooms, lots of bedrooms. So we expect here for the more advanced feature model to do better. Oh, I misspelled something. Oh, I forgot. Here my features model. Sorry about that. That was a little anticlimactic. But if we run it, you see it's 1.38 million. It's a little closer. As you remember from before, the error difference wasn't too big, but here it's a little closer to the true price. So it does a bit better on this house. Now, just to conclude, let's do a even fancier house. So what I'm going to look at, so a third house. So the last house is going to be super fancy. Fancy. And in fact, what we're going to do is take Bill Gates' house. Bill Gates lives in the Seattle area, and try to predict what the house looks like. So it has a lot of different properties, and rather than typing them all in, I'm going to paste them in. So I'm going to paste it here. And this is what Bill Gates' house would have if it were in the data set. It has 8 bedrooms, 25 bathrooms. Bill Gates, you really need to go to the bathroom, apparently. 25 bathrooms, at least that's what I saw online. It has 50,000 square feet of housing. That's about 5,000 square meters. It's a big house. 4 floors, lots of stuff. So that's what his house looks like. We actually don't know what the house is worth because it's never been sold. I guess he doesn't need the money. But here it is. And let's see what that house actually looks like. So, I actually have a little cheat sheet here with a link to an image of his house. So this is a picture of Bill Gates' house. And here we go. Oh, yes. Sorry about that. I forgot. I had to tell it it was a markup. And there we go. So let's see what the model predicts for the price of Bill Gates' house. So I'm going to print what my features model dot predict says for Bill Gates' house. Now, these are GraphLab Create models, and they only take S frames as input. So I have to take that dictionary that I just created to describe Bill Gates' house and convert it to an S frame. So I just type graphlab.sFrame of Bill Gates. This was a dictionary, which is what we defined above here. That's called a dictionary. And I convert it to an S frame and I execute. And it says it predicts it to be valued at $13 million. I don't know. Sounds like a lot, but the house might be worth a lot more than 13 million. Who knows? And that was exciting. We built 2 models of house prices using county data. We explored it, we used it, and we applied it to this task of predicting houses. We even found out what we think Bill Gates' house might actually be valued at. Today we're going to talk about classification, which is perhaps one of the most common areas of machine learning, one of the most used and useful areas of machine learning, and perhaps one of those most intuitive ones as well. So things like figuring out whether your email is spam or not, or whether a document comes from a sports topic, or it's about politics, or it's about entertainment, and so on. But as usual, we're going to start with a use case, which is an exciting one around restaurant reviews. There are many systems for restaurant reviews out there, but today we're going to talk about a pretty new and exciting one that we can build. So it's a new, it's an important day for us, and we're trying to book a Japanese restaurant. And we love Japanese food and want a really cool place to have some Japanese food. But this is Seattle that we live in, and Seattle is really awesome for Japanese food. So there are many, many places for sushi, and in fact there are many that have really good ratings, say 4 stars. So perhaps when I'm thinking about a restaurant to go to, I'm not just thinking about the overall stars of the restaurant, but I'm thinking about how is it in terms of the food, in terms of the ambience, in particular, how is it in terms of the sushi, which is the thing that I really care about. I really love sushi. I want really the best, the freshest fish, and the most awesome, innovative sushi I can get. So when you talk about a positive review for a restaurant, and here's a restaurant that we love in Seattle, a sample review might go something like this. So watching the chefs create an incredible, edible piece of art was really a unique experience. So the experience is really positive, if you think about that aspect of the restaurant. But the review might go on to say, well, my wife tried the ramen and it was pretty forgettable. That means the ramen, not so good. Now, the review continues and says, oh, the sushi was delicious. Easily the best sushi in Seattle. So the sushi was really 2 thumbs up. Now, I don't care about the ramen. I'm not going to this place for ramen. I don't care that this person really didn't like the ramen or his wife didn't like the ramen. What I really care about is good experience and amazing sushi. So this review is just for me. So when I'm thinking about restaurant reviews, I want to understand the aspects of the restaurant that are positive or negative, and really think about which ones of those really affect my interests. So if I look at all the restaurant reviews, I'm going to feed them to this new, really exciting new type of restaurant recommendation system that's going to tell me the experience was good, 4 stars. The ramen was so-so, but who cares? But the sushi, the thing that I really care about, that was 5 stars. And not just that, it's going to give me some interesting feedback. So for example, this is easily the best sushi in Seattle. Now that's where I want to go. So how do we build such an intelligent restaurant review system? Well, we're going to start with all of the reviews, and we're going to break them up into sentences. So each review is composed of multiple sentences, and some sentences cover different aspects of the restaurant. So for example, a sentence that says, easily the best sushi in Seattle. I'm going to feed that sentence through a sentiment classifier. So sentiment classifier is going to say, is this sentence positive or is it a negative sentence? Now we have a sentiment classifier, which can take a sentence and say, is it positive or negative? So how do we build this new kind of cool restaurant review experience? So we're going to take all the reviews and break them into sentences as we discussed, but then I'm going to select the sentences that talk about the aspect I care about. So which ones of these are really about sushi? So not all of them, but a subset of those. Then I feed those sentences through the sentiment classifier, each one of them, and then I average the results. So in this case, all of the sentences were positive, and so I'm going to say this is a 5-star restaurant review in terms of the sushi. And not just that, I can look at the sentences about sushi and look at which ones are most positive. So for example, this one might be the positive, but easily the best restaurant in Seattle, maybe it's the most positive, and I can display those. I can also display the most negative ones. In this case, there's nothing negative to say about the sushi. So we now built a whole new kind of restaurant experience or restaurant review experience using classifiers. So let's dig in and really understand a little bit more what a classifier is and some other applications of classification. So a classifier takes some input X, for example, a sentence from the review or other inputs as we'll see. It pushes it through what's called a model to output some value Y that we're trying to predict. And here it's a class, for example, positive or negative. So positive in the case of a sentiment analysis corresponds to thumbs up reviews, while negative corresponds to thumbs down. But this is just one example of classification. You can look at text, for example, a web page. I want to figure out which web pages interest me, and I can align them to categories. For example, is this about education, a page about education, is it a page about finance, is it a page about technology, and so on. So there's not just 2 categories, there can be 3, 4, or even thousands of categories I'm predicting from. Now, another example of classification, which really has impacted all of our lives, is in spam filtering. Some of you might remember, perhaps in the early 2000s, what spam filters were like. The quality was not very good. Really, they were all hand-tuned things where somebody said, oh, if it has certain words, it must be spam. But the spammers kept changing the words a little bit, adding numbers instead of letters and beating the spam filters. And what really changed the world of spam filtering, it changed it so much that I don't even look at my spam folder. Actually, sorry if your message went to my spam folder, just don't open it. Is machine learning. It's classifiers. They took the input X of the email and they fed it through a classifier that predicted whether it's spam or not, and did that really well. And it does it by not just looking at the text of the email, but it looks at other characteristics. So for example, who sent it? If it's somebody who's a close friend or somebody I have lots of communication with, it's less likely to be spam. The IP address, does that person send it for their usual computer, and so on. Lots of information. So this is another really interesting prototypical application. In computer vision, we do a lot of classification. We're going to take an image and figure out what is in that image. So for example, here, the input X are the pixels of the image. We feed it to a classifier and we're going to predict things like, is this a dog? In fact, it's a Labrador Retriever, Golden Retriever, or a different kind of dog. This is actually my dog, Labrador Retriever. And as we'll see later on in the deep learning module, there's really interesting new ways of doing this with very high accuracy. Now, you can also use classification in medical diagnosis systems. And in fact, this is what your doctor does. They take your temperature, maybe they look at your x-ray, they look at some medical tests, and they try to make a prediction about what's ailing somebody. Maybe they say, no, you're just healthy, or you have a cold, you have the flu, maybe you even have pneumonia. That's a variable Y that's being predicted. What is the disease that's going on? Now, these days, there's really interesting new things around personalized medicine. because the prediction doesn't just depend on the standard measurements, but can be really personalized to me. Can depend on my particular DNA sequencing, which is pretty exciting, and also my lifestyle. So maybe it looks something like that feature on the bottom left, or maybe more realistic, something like this. And so, given all these measurements, we can make an even better prediction at what's ailing me. Now, this idea of classification and of machine learning has really gone much further, even to be able to read your mind. So when I was at Carnegie Mellon, Tom Mitchell, one of my friends and colleagues at his office next door, and he'd come to me and say, we've done this amazing thing. We can take an image of your brain using a technology called fMRI, which is brain scan, and predict when you're reading a word with text, where you're reading the word hammer or the word house. And so it's really reading your mind. But in fact, he went on to do many really interesting things. So for example, if you're looking at a picture of a hammer or a house, but you trained the classifier only on you reading words hammers and house, he was still able to read your mind and figure out what picture you're looking at. So this is yet the next frontier of classification to understand how the brain works. One of the most common types of classifiers is the so-called linear classifier. So let's talk a little bit about that. The question here is how do we represent a classifier? So we start with some sentences. For example, in a sentiment analysis case, we feed it through a classifier, you get a prediction whether it's a positive sentence or a negative sentence. So how does this classifier work? In the sentiment analysis, we can imagine a very simple kind of threshold classifier. Suppose that I take a sentence and somebody tells me, these are all the positive words, great, awesome, good, amazing, and so on. And here's a bunch of negative words, bad, terrible, disgusting, food, and so on. And so what I can do is take the sentence and count how many positive words there are in the sentence and how many negative words there are in the sentence. Just count those. And then say, if the number of positive words is higher than the number of negative words, then we have a positive sentence. But if it uses more negative words, then you have a negative sentence. So for example, if the input sentence that we have is the sushi was great, positive 1, the food was awesome, positive 2, but the service was terrible, negative 1, you have 2 positives, 1 negative, and in the end, positive wins, and so you have a positive prediction. Now, threshold classifiers have some limitations. Where does this list of positive and negative words actually come from? It has to magically come from somewhere. And not just that, words have different degrees of positive and negativeness. So great is more positive than good. Do you want to tune and figure out what's better, great, good, amazing? Is amazing better than great? Who knows? So how do we figure that out? How do we weigh different words? And single words might not be enough to make good classifications. So good food, so the food was good, is positive. The food was not good, is actually negative. And so these are all issues that need to be addressed. The first 2 areas where the positive and negative words come from and how do you weigh them comes from learning a classifier, and we're going to talk about next. The issue of good versus not good is addressed by using more complicated features than single words, and we're going to talk about it towards the end of the module. So a linear classifier, instead of having a list of positive and negative words, actually takes all the words and adds weights to them. So for example, good might have a weight of 1, great might have a weight of 1.5, awesome might have a really big weight of 2.7, while bad might have a weight of -1, terrible might have a negative 2.1, awful might be minus 3.3, because awful is really just awful. And there's words that really don't matter to the sentiment. So things like the, we, where, restaurant, they appear both in positive and negative sentences, so they get weight 0. Suppose somebody magically told you what the weight of each word were. We're going to talk about it in a little bit, how those get learned by the classifier. But given those weights, how do we figure out if the sentence is positive or negative? Here we use the idea of scoring. So for example, take the sentence. The sushi was great, the food was awesome, but the service was terrible. Let's score that sentence. So we're going to compute this the score of the input sentence X. So in this case, you get from great, you get positive 1.2. From awesome, you get another 1.7. But from terrible, you get a minus 2.1 right here. And so the grand total here is 2.9 minus 2.1, which is 0.8. And the key here is that since the score of the sentence is greater than 0, we're going to predict that it's a positive sentence. If the score were the opposite, if the score of X were less than 0, then we'd have predicted it's a negative sentence. So this is how a linear classifier works if you know the weights of each word. And this is called a linear classifier because the output is basically the weighted sum of the inputs. Just weight what features appear, what words appear in the input. So we're working with a simple linear classifier to start out with. So in summary, given a sentence and given the weights for that sentence, what we do is compute the score, which is the weighted count of the words that appear in the sentence. And then we say, if the score is greater than 0, we predict y hat to be positive, while if the score is less than 0, we predict it to be negative. And that is a linear classifier. So classifiers are really trying to make decisions as to whether a sentence is positive or negative, or whether a set of lab tests plus x-rays plus measurements lead to a certain disease like flu or cold. That's a decision that needs to be made. So let's talk a little bit about how classifiers, especially linear classifiers, make decisions. To understand decision boundaries, suppose you only had two words with non-zero weight. You have awesome with positive weight of 1 and awful, which is just awful, so it has a negative weight of 1.5. If you have this situation, then the score is going to be 1 times the number of awesomes in the sentence minus 1.5 times the number of awfuls. So we can plot this on an axis. There's the awesome axis, and then there is the awful axis. So for example, the sentence, the sushi was awesome, the food was awesome, but the service was awful. Then that has 2 awesomes and 1 awful. It's plotted in the point 2,1 on the axis. And similarly, for something that has, say, 3 awfuls and 1 awesome, for something that is all awesome, so 3 awesomes is at the point 3,0, and so on for other sentences. Now, let's understand a little better how we score the sentences and what does that imply about our decisions. So, for example, take the point 3,0 that has 3 awesomes, no awfuls. 3 awesomes gives you a positive prediction because the score is greater than 0. And that is true for every point really on the bottom right of the axis. While the points on the top left all have score less than 0, so for example, the point 3 awfuls, 1 awesome is got score less than 0, so those get labeled negatively. And in fact, what separates the negative predictions from the positive predictions is the line that defines the places where I don't know what's positive and what's negative, and that's the line where 1 times awesomes minus 1.5 times awfuls equals to 0. And that's the line where I don't know, the prediction is uncertain, and so we call that the decision boundary. Everything on one side we predict as positive, everything on the other we predict as negative. Now notice that that decision boundary, 1 times awesome minus 1.5 times awful equal to 0 is a line. And so that's why it's called a linear classifier. It's a linear decision boundary. So decision boundaries are what separate the positive predictions from the negative predictions. So in the case of just 2 features, we see this is just a line. But that situation will differ as we increase the number of features. So in 2 dimensions, a linear function is a line. In 3 dimensions, we have 3 words, for example, that have non-zero weight, everything else has 0 weight, then what we get is a plane. And so it's a little hard to draw in 3D, but the positive predictions here are above the plane, and the negative predictions here are below the plane, and the plane is somehow inclined in the space. Now, when you have not just 3 non-zero words, but in real applications, you're going to have tens of thousands of words with non-zero weights. And in that case, we call those hyperplanes, those really high dimensional separators, called hyperplanes. Now, of course, you can use more than linear classifiers. You can use more complex classifiers. And those, still having lines or hyperplanes, they have more complicated shapes or squiggly separations. And we're going to learn more about that in the classification course. In the regression model, we talked about predicting house prices and fitting a regression model for that. And we measure the error in terms of sum squared errors. Here in classification, our errors are a little different because we're talking about what inputs we get correct and which inputs we get wrong. So let's talk a little bit about measuring error in classification. So when I learn a classifier, I'm given a set of input data. So these are sentences that have been marked as, say, positive or negative sentiment. And as in regression, we split it into a training set and a test set. I feed the training set to the classifier I'm trying to learn, and that algorithm is actually going to learn the weights for words. So for example, it's going to learn that good has weight 1.0, awesome 1.7, bad minus 1.0, and awful minus 3.3. And then these weights are going to be used to score every element in the test set and evaluate how good we're doing in terms of classification. So let's talk about what that evaluation looks like. Let's discuss how we measure error, in fact classification error, when we're doing this classification. So we're giving a set of test examples of the form sushi was great is a positive sentence, and we're trying to figure out how many of these test sentences we get correct and how many do we make mistakes on. So what we're going to do is take the sentence sushi is great and feed it through the classifier, through the learn classifier. But we don't want the learn classifier to actually see the true label. We want to see if it gets the true label right. So we're going to hide that true label. So the sentence gets fed to the learn classifier while the true label is hidden. And now given the sentence, we're going to predict y hat as being positive. So we believe this is a positive sentence, and so we've made a correct prediction. So the number of correct sentences goes up by 1. Now let's take another sentence, another test example. So let's say you say, the food was okay as a negative sentence. So that's a bit of an ambiguous sentence, but it's been labeled as negative in the training set. So now I feed the sentence to the classifier, I hide the label, and let's see what the classifier does. In this case, because the food was okay, it can be billed as positive, maybe it makes a prediction that this is a positive sentence. I've made a mistake because the true label is negative. So we say, hey, mistake was made. We now have one more mistake. So we have one correct classification and one mistake. Now we do this for every sentence in the corpus. There are two common measures of quality in classification. So for example, one of them is the notion of error. So error measures the fraction of the test examples that we make mistakes on. So what we just do is say, out of all of the sentences that are classified, how many mistakes they made, so number of mistakes, and I divide that by the total number of test sentences. So for example, if there were 100 test sentences and I made 10 mistakes, then our error will be 0.1 or 10%. Now, the best possible error that I can make is 0, basically. I make no mistakes. Now, it's common to, instead of talk about error, to also talk about accuracy of your classifier. So accuracy is exactly the opposite of that. So in accuracy, instead of measuring the number of errors, we measure the number of correct classifications. So the ratio here is number of corrects divided by total number of sentences. And unlike error, where the best possible value was 0, in terms of accuracy, the best possible value is 1. I got all the sentences right. And in fact, there is a really natural relationship between the two. We know that error is equal to 1 minus accuracy, and vice versa. We've discussed error and accuracy as ways to evaluate a classifier. Now it's very important to understand the accuracies or errors that you're actually getting from a classifier. Really think deeply about whether those are good errors or good levels of accuracy in your situation. So for example, one of the common mistakes you might make is to say, how good is my classification at all? When you build a classifier, the first baseline comparison you should do is against random guessing. So for example, if you have a binary classification problem, like is this sentence of positive or negative sentiment, then just random guessing is going to give you 50% accuracy on average. So you better beat 50%. If you have k classes, so for example, if you have 3 classes, you're going to have a random guessing accuracy of 33%. For 4 classes, it will be 25%. For k classes, it will be 1 over k. So at the very least, you should beat random guessing really well. Because if you don't, then your approach is basically pointless. Now, even beyond beating random guessing, you should really think deeply about whether your classifier, even if it looks really good, is it really meaningfully good? So for example, suppose you have a spam predictor that gets 90% accuracy. Should you go brag about it? Is that awesome? Well, it really depends. So in the case of spam, not so good, because in 2010 data shows that 90% of the emails ever sent were spam. 90% of the emails. So if I just guess that every email is spam, what accuracy do I get? 90%. This is a problem where this is what's called majority class prediction. So I just predict the class that's most common, and it can have amazing performance in cases where there's what's called class imbalance. One class has much more representation than the others. Spam is much more representative than regular good emails. And so you have to be very cautious and really look at whether you have class imbalance when you try to figure out whether your accuracy is good. And of course, this approach also beats random guessing if you know what the majority class is. So you should always be digging into your problem and understanding, really thinking about the predictions you're getting and whether that accuracy is really meaningfully good for your problem. So ask yourself questions like, is there class imbalance? How do I compare against baseline approaches like random guessing, majority class, and really fancier things than that? And most importantly, think about your application and ask yourself, what is a good enough accuracy to make my users really happy? So if in spam filtering, if your accuracy is not that good, then there will be important messages going to the spam folder, and that could be a really bad thing. We've talked about accuracy and errors that a classifier might make, but there are different kinds of errors. So these kinds of errors are called types of mistakes. It's important to look at the types of mistakes a classifier might make. And one way to do that is for what's called a confusion matrix. So let's take that in a little bit. So we're talking about the relationship between the true label and whatever classifier predicts, so the predicted label. So let's say that if the true label is positive and we predict a positive value for that sentence, we call that a true positive because we got it right. Similarly, if the true label is negative and we predict that negative, we call that a true negative. That's good because we got that right. Now there's 2 kinds of mistakes that I can make. So for example, if the true label is positive, but we predict it as negative, we call that a false negative. We said it was negative, but that was false because it was positive. Similarly, if the true label is negative, but we predict it as positive, we call that a false positive. It was negative, but we predict it as positive. And false positives and false negatives can have different impacts on what can happen in practice with your classifier. So let's look at a couple of practical examples of that. So let's look at 2 applications and what the cost has of false positives versus false negatives. So if we consider spam filtering, a false negative is an email that was spam but went into my folder. You thought it was not spam. So that's just annoying. I got another spam email in my inbox. Maybe it's bad but not super bad. However, if you look at a false positive, That's an email that was not spam, that got labeled as spam, went to my spam filter, I never saw it, I lost that email forever. That has a higher cost. Now we can also look at medical diagnosis or other applications as a second application. So what's a false negative in medical diagnosis? False negative is there's a disease that I have, but it didn't get detected. So the classifier said it was negative, I don't have the disease. So in this case, the disease goes untreated, which could be a really bad thing. But the false positives can also be a bad thing. That is, I classify as having the disease where I never had the disease. And in this case, I get treated potentially with a really bad drug with lots of side effects for a disease that I never had. So it's a little bit unclear what's worse, having a false positive or false negative. In medical applications, it really depends on the cost of the treatment and how many side effects it has versus how bad the disease can be. Now, this relationship between the true label and the predicted label, false positives and false negatives, is called the confusion matrix, this matrix that we just drew. So for example, let's say that we have a setting with 100 test examples. And we have, of those, 60 are positive and 40 are negative. So there's a little bit of class imbalance, but not too much. So of those 60 true positives, if I say I got 50 of them correct, while of the 40 true negatives, I got 35 of them correct. Let's see what we've learned. So out of the 100 examples, I got 85 correct. So we can talk about accuracy. Accuracy is 85 correct over 100, which is 0.85. And we can also discuss the true positives and the true negatives. Sorry, the false positives and the false negatives. So of the positives, I got labeled as negative. That's a false negative. And that was 10. I had 10 false negatives. And on the other hand, of the true negatives, we get 5 false positives. So in this example, we got 85% accuracy. We got a higher false negative rate than we had a false positive rate. Now those words, false positive, false negative, apply only for binary classification for 2 classes, but the ideal confusion matrix works well even when you have more classes. So let's talk about a simple example of that. So let's say that I have 100 test examples, and this is for medical diagnosis. So there's 3 classes, healthy, cold, or flu. And of the 100 test subjects, we had 70 with that were healthy, 20 that had cold, and 10 that had the flu. And let's suppose that we got 60 correct for healthy. We got 12 correct for cold, and we got 6, 12, 8 correct for flu. So at the total, our accuracy here was 80, which is 60 plus 12 plus 8 divided by 100. So that's 0.8, 80% accuracy. But we can talk about the false positives, the false predictions. So from healthy, there were 10 mistakes. And we can say it's more common to confuse healthy with having a cold than it is with having the flu, because the flu is a more complex disease. So we might have those 10 mistakes, 8 were confused with cold and 2 were confused with flu. Cold can go both ways. So we made 8 mistakes. Maybe you can say half of them got confused with healthy and half of them got diagnosed with something stronger, the flu. Well, of the 2 mistakes for the flu, then maybe you would say that we made no mistakes as healthy. Nobody that came in with a flu was thought, oh, you're healthy. But 2 of those 10 were thought to have just a cold and not the flu. So this is an example of a confusion matrix. We can really understand the types of mistakes being made, and we can interpret those. And this is a really important thing to do in classification. In the regression module, we talked about the relationship between error or accuracy and the complexity of the model. Let's talk a little bit about the relationship in terms of the amount of data you have to learn. and really explore the question of how much data do we need to learn. And this is a really difficult and complex question in machine learning. So, of course, the more data you have, the better, as long as the quality of the data is good. Having bad data, lots of bad data, is much worse than having much less, much fewer data points, but really good, clean, high-quality data points. Now, there's some theoretical techniques to analyze how much data you need. Many of those help you understand kind of the overall trends, but really tend to be too loose to use in practice. In practice, there's some empirical techniques to really try to understand how much error we're making and what that kind of error looks like. And in the follow-up courses, we're going to explore those techniques much further, but let me give you a little bit of guidance and a little insight on what I can do within the classification setting. Now, an important representation for this relationship between data and quality is what's called a learning curve. So a learning curve relates the amount of data that we have for training with the error that we're making. And here we're talking about test error. Now, if you have very little data for training, then your test error is going to be high. But if you have a lot of data for training, your test error is going to be low. And now the curve is going to get better and better as you get more and more and more data. Whoops, didn't go through that point, so I'm going to just erase it. And here we go. This is an example learning curve where the quality is getting better as we add more data. Now you may ask, is there a limit? Is this quality just going to get better and better forever as you add more data? Now we know that the error is going to decrease as we add more data, the test error. However, there's some gap here. And the question is whether that gap can go to zero. And the answer is in general no. This gap is called a bias. So let's discuss a little bit what this bias or this gap is. So intuitively, it says even with infinite data, the test error will not go to zero. So let's understand why a little bit. More complex models tend to have less bias. So if you look at a sentiment analysis classifier that we've been building, if you just use single words like awesome, good, great, terrible, awful, it can do okay. Maybe it do really well, maybe it just does okay. But even if you have infinite data, even with all the data in the world, you're never going to get this sentence right. The sushi was not good. Because you're not looking at pairs of words, you're just looking at the words good and not individually. And so more complex models that, for example, deal with combinations of words, for example, there's something called the bigram model where you look at pairs of subsequent words like not good. Those models require more parameters because there's more possibilities. They can do better. They might have a parameter for good, say 1.5, but not good, say minus 2.1, and actually get that sentence, the sushi was not good, correctly. So they have less bias. They can represent sentences that couldn't be represented otherwise, so they're potentially more accurate, but they need more data to learn because there's more parameters. There's not just parameter for good, there's now a parameter for not good and all possible combinations of words. And the more parameters your model has, in general, the more data you need to learn. So let's go back to our example. We talked about the effect of amount of training data on the test error. So let's say that I'm building a classifier using single words. And the question is, how does that relate to a classifier based on pairs of words? Now, for a classifier based on bigrams, when you have less data, it's not going to do as well because it has more parameters to fit. But when you have more data, it's going to do better because it's going to be able to capture settings like the sushi was not good. And so the behavior you're going to get is something like this. And at some point, there's a crossover where it starts doing better than the classify with single words. But notice the bigram model still has some bias here. Although the bias is smaller, it still has some bias. So far we talked about classification in terms of just predicting, is this a positive sentence or a negative sentence, is it email spam or not spam, but in general you want to go a little bit beyond that and ask about what is the probability that this email is spam. So how confident am I on the prediction? Instead of just looking at positive and negative, I want to know how sure I am about the prediction. So for example, if you take a sentence like, the sushi and everything else were awesome, that's a definite plus, definitely positive. However, the sushi was good, the service was okay. It's probably a plus, but I'm not so sure, it's not as definite. And so what a classifier will often do is not just output is positive or negative, but output how confident or how sure it is. One way to do that is to talk about probabilities. So here we have to put the probability of being a positive or negative sentence given the input sentence X. So the output label, what's the probability output label given the input sentence? So for example, for the top example there, instead of saying a definite plus, we say that the probability that it's a plus given X input sentence is 0.99. While in the second one, the probability of being a plus given X is only 0.55 because I'm kind of uncertain about things. Predicting probabilities or level of confidence is extremely important. And as we'll see in the classification course, it allows you to do many things. So for example, when we know the probability, you can make decisions like what is a good decision boundary that trades off false positives and false negatives and balance between the two. Now we've seen classification in a wide variety of settings and how it can really be used to predict a class like positive or negative sentiment from data. In the regression section, Emily talked about this block diagram that really describes how a machine learning algorithm iterates through its data. So now let's take this same block diagram and work through it and describe how it works out in the case of classification with a sentiment analysis. So how does it look for classification for sentiment? So in this case, the data is the text of the reviews. So for each review, the text of the review associated with a particular labeled sentiment. From that text of the review, we feed it through a feature extraction phase, which gives us X, the input to our algorithm, and this X here is going to be the word counts. So word counts for every data point, for every review. Now our machine learning model is going to take that input data, so the word counts, as well as some set of parameters, which I'm calling here W hat, which are the weights for each word. And by combining these two, we're going to output a prediction. So if the score is greater than 0, it's going to be positive. If the score is less than 0, it's going to be negative. So this output here is the predicted sentiment. And if we're just using the model, we would be done here. But really, in the machine learning algorithm phase, we're going to evaluate that result and then feed it back into the algorithm to improve the parameters. So we're going to take the predicted sentiment, y hat, and compare it with the true label for the sentiment. So the sentiment label for each data point. So that's going to feed in. And our quality measure here is going to be classification accuracy. Classification accuracy. And the machine learning algorithm, which we're going to discuss in more detail in the classification course, is going to take that accuracy and try to improve it. And the way the improvement works is by updating the parameter w hat. And that's what the cycle of a machine learning algorithm for classification would look like. In this module, we've seen how to do classification. We've looked at various examples of where it can be applied. We talked about a few models for building classification, especially in the context of sentiment analysis. We saw some live demos, and we even built a notebook where we built a classifier from data and analyzed it. And with this knowledge, you're ready to build an intelligent application that uses a classifier at its core. In this module, we talked about building sentiment analysis tools using classification. And now in this notebook, we're actually going to go ahead and build one of those things. So we're going to build a sentiment analyzer for products. So let's go ahead and get started. Okay, so here we are on an IPython notebook as usual. And again, I'm going to hide the header. Before I hide the header, I'm going to change its name. So let's rename the notebook. So I'm going to call this the analyzing product sentiment, since this is the notebook we're building. And I'm going to hide the header, and I'm going to hide the toolbar, just to have a little bit more space. And we're going to be using GraphLab Create today, so I'm going to import GraphLab to get ourselves started. Here we go. So the first thing that we're going to do is read some data. So let's read some product review data. So let me read some product review data. And this is a real data set that we're going to read. So I'm going to create an S-frame called products, which uses GraphLab S-frame from a local file. I've downloaded the data. You're going to download the data too. And this is some Amazon baby product data set. Okay, we've downloaded that data. And so the first thing that we're going to do is do a little bit of data exploration. So let's explore this data together. And this is fun. So we have some product data. So let's just look at the head of this table. So the head is just the first few lines of this table that I've loaded up. And so, as you can see, it's composed of three things. The name of the product, so Planet-Wise flannel wipes, pretty good product. The review, this flannel wipes are just okay, but in my opinion, something. And the rating is 3, and it's out of 5 stars, so 3 is kind of a middle of the road rating. While the Planet-Wise wipe pouch, this review really liked it and gave it a rating of 5. So this is the data set that we're working with. So let's take a look at what products we have. So let's look at what reviews we have for different product names. And here we're going to use the canvas again to do a little bit of visualization. And so as with before, I'm going to do graphlab.canvas. I'm going to set the target to be my IPython notebook, so it will show up right here on the IPython notebook as we're building this. Now we can take one of the columns of this S-frame of the products. So for example, let's take the name of the product, and we can just hit .show on it, and that's going to show a histogram of the different names of the different products in this data set. So for example, right here, so you see that this particular product, Vuli Sophie something, gets the most reviews, 785 reviews, as compared to like simple wishes, something, 562 reviews. And you can see that the number of reviews go down. Fisher Price products, 489, 450. This is different baby products here that we're analyzing. And you see the histogram of the different reviews of different products, number of reviews. So let's visit that first, Woolly Sophie. What is that? So let me tell you a little bit more about that product. So let's explore the so-called Woolly Sophie. And this is an extremely popular product. So it's actually, I happen to have one right here. This is Woolly Sophie, the giraffe teether. So it's a little plastic giraffe. It's the most gifted product for babies on Amazon. And it's a teether, which means like babies like to chew on it. So lots of reviews for this giraffe for babies to chew on. And it's made out of plastic and it squeaks. So this is what we're going to talk about a lot today, this little giraffe. Now, let's look at the reviews for this particular giraffe. So I'm going to call it giraffe reviews. And what I'm going to do, I'm going to take all those products that I have, all those product reviews, and I'm going to select, this is another filter, I'm going to select those rows where the product name is equal to the name of this particular giraffe. So this is Woolly Sophie, the giraffe teether. This is the product that we've been talking about. So if we take a quick look here, if I ask for the length of this new thing, giraffe reviews, this new table, you'll see there's 785 reviews for this plastic toy, little teether. So 785 reviews, and let's look at the ratings. So I'm going to take the giraffe reviews, the ratings, just for this particular product, and I'm going to do a dot show on it, like we've been doing. But I want to look at a particular view called the categorical view, which is going to give me categorical view, which is going to give me a histogram, a sorted histogram of the different reviews and how many scores we got. So if you take a look at this little histogram here, you will see something kind of interesting. People love this thing. 535, the reviews were 5 stars. This is a product, 535 5-star reviews. Then the next most common is 4 stars, then 3 stars, then it jumps down to 1 star, and finally 2 stars. So a good sizable number of people really hated this product, but most people loved it. So it would be fun to do a kind of sentiment analysis to try to understand what are the really negative reviews, what are the really positive reviews, or what is reviews talking about, just like we discussed in the lectures in this module. So to do that, we're going to build a sentiment classifier. Build a sentiment classifier. And I'm going to put a pound here to make it a nice title. So this is our next task here. And so when you build a sentiment classifier, you're talking about positives and negatives. So thumbs down and thumbs up. But if you remember, our product ratings were not about positive and negative. They were numerical things. So for example, if I take all the products and I'll take the rating column and I do a dot show as we did above just for the giraffe, but do a dot show for everything with the view equal to categorical, we're now building a histogram for all of the reviews, and if you take a quick look at it, you'll see that most reviews are positive across the board. 107,000 reviews are 5 stars. So most people review positively. Just write reviews about products they like. They don't typically write reviews about products they don't like. Then the next set of reviews, 33,000 is 4 stars, then 3 stars. And again, a lot of people write really bad reviews, 1 star. 2 star, why would you give a review product 2 stars? You might as well just give him 1 star if you really hated it. And this is what we observe in this histogram. But again, for sentiment analysis, we have to define what's thumbs up and what's thumbs down. And so I'm going to make an arbitrary choice here. Let's say that things at 4 or 5 stars are things people liked. So those are positives. Things that 1 and 2 stars are negative. But the things that are 3 stars, those are kind of in the middle, so let's just throw those out. So we're going to do a little bit of what we call kind of data engineering, just defining what is a positive and negative sentiment. So let's do that right now. So in the subsection, we're going to define what's a positive and a negative sentiment. And what I'm going to do first is ignore all 3-star reviews. And the way to do it is by saying, okay, I'm going to take the products table, the variable products, and I'm going to just select everything out of the products table whose rating was not 3. So out of the products table, select all products whose rating was not equal to 3. So that was our first step in our little data engineering task. And now the next step in this task is to actually define what's thumbs up and thumbs down. So I'm going to say a positive sentiment equals 4-star or 5-star reviews. So let's go ahead and add a new column to our table that defines the actual sentiment. So products, new column called sentiment. It's going to be a binary column, 0 or 1. And the way we're going to define a column is I'm going to say of the products rating, is it greater or equal to 4? If it's greater or equal to 4, it's going to get a 1. And if it's less than 4, it's going to get a 0. And so now, if I take another look at my products table, so head, you should see that I've added a new column on the right called sentiment. And most of the sentiments are positive, as we saw earlier, but many are negative, 0. Okay, now we're ready. We're finally ready to train our sentiment classifier. Let's train the sentiment classifier. And we're going to do this in 2 steps. First, we're going to do a train test split of the data. So I'm going to compute the training data. I'm going to split the data into training data and test data, just like Emily talked in the regression class and just like we did in the regression notebook. So we're going to use, we'll take this product table, products, and then we're going to do that random split. So, products, and I'm going to do that random split where we're going to do 80% for training, 20% for testing. And just so that you can reproduce this at home, I'm going to do the seed equals to 0, just like we discussed in regression. Normally you wouldn't do this, you pick another random seed, but I want the random seed to be the same, so when you do it, you get exactly the same results I did. So this is my first step, the train test split on this data set. And now we're ready. We're going to build that famous sentiment model. And here we're going to use GraphLab, and we're going to use a particular classifier called the logistic classifier. And in the course on classification, we're going to learn a lot about different kinds of classifiers, like logistic regression, this one, support vector machines, decision trees, and others. But let's start with just the logistic classifier. And you can, just like in regression, you can type .create after the name, and it will actually create a classifier for you. And as input, it takes just a few parameters. So we're going to take the training data as one parameter. Then we're going to see that the target, the thing we're trying to classify, is the sentiment column. And then we're going to have to tell it what features to use. So for the features, we're going to use just the word count column. So this is the new column that we created above for word counts. And I'm going to give it a validation set. So the validation set is going to be my test data. So validation set equals test data. Okay. So now we execute the cell, and we should be building a sentiment classifier model. And you're only going to take a few seconds, and here we go. It's done, and you will see the iterations you went through going through the data, and the validation accuracy as it goes along. It seems to be getting better and better. But let's actually do a real evaluation. Our next step is to evaluate the sentiment model that we've built. Now, we just talked in this module about classification error, precision, false positives and false negatives, and we're going to explore that idea right here in this demonstration in this notebook. So, the sentiment model has a function called evaluate, and that function evaluate allows you to evaluate its quality on some test data, and we're going to provide a particular metric, and this metric is called the ROC curve, and we're going to learn a little bit more about the ROC curve next. But the ROC curve is a way to explore the false positives and false negatives and that confusion matrix that we discussed. Now here it shows you the results of the evaluation. It's a little hard to see in text, so let's do a little visualization of it. Again, using Canvas. So we can use sentiment model.show, and what we're going to show, the view that we're going to use is going to be the evaluation view. And here we go. Okay, now this is really cool. We've built a few things. So this is a precision recall. This is a ROC, what's called the ROC curve. Is a curve that trades off false positives with true positives. Let me explain that a little bit. But first, let's look at these numbers over here. So this is the confusion matrix. The number of true positives, the things that we got right that were true, is 26,455. So right here. The number of true negatives was only 4,000, so 3,965. So this is a highly unbalanced case. And then the number of false positives and number of false negatives is about the same. The overall accuracy was 91.1%, so 0.911. And we also discussed a few metrics like precision recall and F1 score, which we're going to learn more about later in the course and later in the specialization. Now, the thing about the false positives and false negatives is that there is a very natural way to change the threshold of what we believe the transition from negative class to positive class should be. So, and this is what this threshold shows on the right. But let me first show it on the curve here. So you can see it is possible for me to get, for example, a very high true positive rate, so 0.4, a very low 0.4, if I don't allow myself to get any false positives. So if I'm very worried about false positives, I can be very conservative, get no false positives, but again, not capture many of the true positives and make other mistakes. And you see, as you go through the curve, there's a kink here. This is the point where you get not too many false positives, but a lot of true positives. And then over on this end, you get every true positive, but you get a lot of false positives. how do you get every true positive but get a lot of false positives? You just say every data point is positive. Then you get all the true positives, but you also make a lot of mistakes. And we'll discuss more of this when we talk about the precision recall curve. But nicely, you can change the threshold over here and walk that curve up there, as you can see. And so, for example, at the far end on the right, you see that the true positive rate is really high. There's no false positives, but there's no true negatives. So there's no false negatives, no true negatives. You just got everything right. And then you can slide it just the other way. So you can play with this and really kind of get a good sense of what this curve really means, the ROC curve. And that's the evaluation that we're going to be doing. We've built a model. We understood its accuracy about 0.911%. Let's go and actually use this model for something actually quite cool. So what I'm going to do is apply the model, learned model, to understand sentiment for our friend the giraffe. So here we go. Let's understand it a little bit. So here's what I'm going to do. I'm going to take those giraffe reviews that I built a little bit earlier, and I'm going to create a new column to this giraffe reviews called my predicted sentiment. And this predicted sentiment is going to come from taking the sentiment model that we built, the sentiment model, and oops, this autocomplete was a little slow, sorry about that. We have a little glitch there. So, okay. We're going to take the sentiment model and we're going to call this function predict on it. And we're trying to predict how does it feel about the giraffe reviews. So how do you feel about my friends, the giraffe reviews? And the output, and this is a key thing, we're not just going to output the 0, 1, whether I predict the sentiment to be 0 or 1. I'm going to say output probability. And if you remember, we just talked about this in the module, that by outputting probability, you can get a more fine-grained estimate of what the prediction looks like. So we just ran it, and just let's take a quick look at what this new giraffe reviews look like. So let's look at the head of this table. And you'll see that now we had the name of the product, the review, the rating, the word count, and I added another column called the predicted sentiment. And for some reviews, it's really high, 0.999, 0.99. And here's a review that's pretty low sentiment. There should really be a large warning on the they don't like it for some reason. Now let's try to understand. Let's look at the reviews and see what reviews are positive or negative. And let's see what the people are saying about the product. So here's what I'm going to do. We're going to sort the reviews based on the predicted sentiment and explore. And the cool thing here is the predictive sentiment is a much more fine-grained description of whether a review is positive or negative. The stars are really skewed, 5 stars, 4 stars, 3 stars, 1 star, but it doesn't tell you how far along the spectrum you are. But now that we have these numbers, this extra column, we can do a lot more. So I'm going to take this giraffe data and I'm going to sort it. So all I have to do is take the same value, and I'm going to call the function sort on it, and you have to say what column you're sorting based on. So we're going to sort based on this new column that we call predicted sentiment. And one little trick here, we're going to say ascending is equal to false. So instead of sorting that ascending order, it's going to sort in descending order, starting from the most positive reviews down to the most negatives. Now that we've sorted it, we're going to just show the first few lines of the table, and what you should see is that the reviews are now sorted based on that sentiment. So the very top here, we have the most positive one has predicted sentiment of 1.999, and they're all sorted. So for that first review, they had product sentiment predicted as 1. Let's take a look at that review. So I'm going to look at the giraffe reviews. The first one is 0, the index 0, and let's look at the actual text of the review. Okay, I'm going to read this to you a little bit. It says, "Sophie, oh Sophie, your time has come. My granddaughter Violet is 5 months old and starting to teeth. What a joy for little Sophie. Little Sophie brings Violet." Oh, Violet really loves Sophie. Sophie is made of very pliable rubber that is sturdy but not tough, and it's quite easy for Violet to twist unheard positions and put it in her mouth. And okay, that's what a positive review looks like. She's writing a poem about Sophie. Let's look at the second positive review here. So this is the for element 1, so it's the second element on the table, and let's look at what that review looks like. And here's what it says. "I'm not sure why Sophie is such a hit with the little ones, but my 7-month-old baby girl is one of the adoring fans. The rubber is softer and pleasant to handle. My daughter enjoys chewing on it, on the legs, nubs of the head, so these ears get chewed, and so on. She really loves it, and it loves that it's squeaky. So apparently it's a big hit." So this is 2 positive reviews. Now let me show you a little Python trick which we can use to show the most negative reviews. So the most negative reviews are at the bottom of the table. So we could ask, what is the length of the table, and find the last element and so on. But with Python, we can do this really easily. So let me show you what's happening next. Show most negative reviews. So we can take this table and just index it with a negative number, -1. And what that does, it goes to the end of the table. So -1 is the last element, -2 is the second to last element, and so on. So let's look at the most negative review for our giraffe. And I forgot to put a quotes here. So let's just do that and execute. Okay, here's a negative review about poor Sophie. "My son loved Sophie. I bought one for every baby shower I've gone to. Now my daughter, 6 months old, just today nearly choked on it, and I'll never give it to her again." So the problem is, this person's daughter is really scary, almost choked by trying to swallow this giraffe. And so you see a negative review about somebody talking about how this giraffe, which is a lovely chewing toy, is also a choking hazard. Let's look at the second most negative review. So again, giraffe, and -2, second most negative review, and we'll take a quick look at it. So one thing that people don't like about it is it might be a choking hazard. So let's see what this one says. "This children's toy is nostalgic and very cute." That sounds pretty positive. Even the second most negative review starts pretty positive. However, the distinct rubber smell and very odd taste. Yes, I tried it. So this person tried to chew his or her kid's toy that my baby did not enjoy. So apparently the rubber smells, and this person wasn't able to chew it, clean it, and the kid did not like it, and they overpaid for this toy. So the second thing that people complain about is that this is a smelly toy. It smells okay to me, but could be an issue. Okay, so now in a few lines of code, we build a sentiment analysis system that can actually look at reviews and really sort them and show really positive and negative aspects of this particular product.
Okay, so in this module, we're going to talk about clustering and similarity. And the point here is the fact that often we have lots of observations and we want to infer some kind of structure underlying these observations. And in this case, the structure we're going to talk about is groups of related observations, or clusters. And as with all of our modules, we're going to motivate everything with a real-world application, a case study. And in this case, we're going to talk about a task of retrieving documents of interest. So the first thing we need to describe is how are we going to represent the documents that we're looking at. Okay, so perhaps the most popular model to represent a document is something called the bag of words model, where we simply ignore the order of words that are present in the document. And the reason it's called a bag of words model is we think of taking a bag, throwing all the words from that document into the bag, shaking it up, and the new document we've created with the words all jumbled up has exactly the same representation, as I'll describe, as the original document where the words were ordered. And what we're going to do, instead of considering the structure, the order of the words, is we're simply going to count the number of instances of every word in the document. So let's look at a specific example of this. And so in this document, we're going to imagine that there's just one sentence, and that sentence says that Carlos calls the sport football, Emily calls the sport soccer. Actually, I guess that's really two sentences, but that's the entire document. And what we're going to do to count the number of instances of words in this very short document is we're just going to look at a vector, and this vector is defined over the vocabulary in whatever language we're looking at. So maybe one word in our vocabulary is the name Carlos. Another place in this vector is the index for the word sport. And then somewhere else we have the word football, luckily in our English vocabulary that I'm writing here. And then let's say Emily is this last entry. What words are we missing? We're missing the word calls. And of course the word the. Okay, so how many instances of Carlos? Well, there's only one. How many instances of the? We have two of the, two of calls, two of sport, one of football, and I forgot the word soccer, one word of Emily, and let's just throw soccer in here, imagining this was the index, and this would be our word count vector with, for this document, every other entry would be 0, and all these other entries represent all the other words that are out there in the vocabulary, like the word cat and dog and tree and every other word you can think of. So it's a very, very long and sparse vector that counts the number of words that we see in this document. Okay, so we talked about this representation of our documents in terms of just these raw word counts, this bag of words model. And now we want to talk about how we're going to measure the similarity between different documents, because we're going to use that in order to find documents that are related to one another. So if like we talked about before, Carlos is reading an article, what's another article he might be interested in? Okay, so imagine that this is the count vector we have for this article on soccer with this famous Argentinian player, Messi. And then there's another article here that I'm showing in blue, and the associated word counts, and this article is about another famous soccer player, Pele. Is that right?
Pele.
Pele. So when we think about measuring similarity, what we can do is simply look at an element-wise product over this vector. So for every element in the vector, we're going to multiply the two elements appearing in these two different count vectors and add up over all the different elements in this vector. So here I've done this math where we have 1 times 3, all the other elements multiplied to 0 except at some point that fifth entry in the vector, we have 5 times 2. And if we do this multiplication over the whole vector, the sum of these terms is 13. So that measures the similarity between these two articles on soccer. But now let's compare to another article, which happens to be something about a conflict in Africa. And so I'm providing the examples of word counts that appear in this article. And what we see is when we go to measure the similarities between these articles using the method that I described of element-wise product and then adding, that the similarity here in this case is 0. Okay, so let's talk about an issue that arises when we use these raw word counts to measure the similarity between documents. So to do this, let's look at these green and blue articles that we had before. And so I'm repeating the word count vectors that we had. And what we calculated before was the fact that the similarity between these two articles that are both about soccer is 13. Okay, but now let's look at what happens if we simply double the length of the documents. So now every word that appeared in that original document appears twice in this twice as long document. So the word count vector is simply 2 times the word count vector we had before. So when we go to calculate the similarity here, what we see is now the similarity is calculated to be 52. So let's think about this. What we're saying is that 2 documents that are related to each other in the same way as before. They're both talking about the same 2 sports, but one just is replicated twice, is a lot more similar. We would say, yes, Carlos is a lot more interested in this longer document than what happened when Carlos was reading the shorter documents. So this doesn't make a lot of sense when we're trying to do document retrieval, and it biases very strongly towards long documents. So let's think about how we can cope with this. So one solution is very straightforward, where we're simply going to normalize this vector. So we take this word count vector, and we're going to compute the norm of the vector. And so if you guys remember computing the norm of a vector, we simply add the square of every entry in the vector and then take the square root. So in this case, we have the square root of 1 squared plus 5 squared plus 3 squared plus 1 squared. And that happens to be the number 6. And so the resulting normalized word count vector is shown on the bottom of the slide here. And what this does is it allows us to place all of our articles that we're considering, regardless of their length, on equal footing, and then use this normalized vector when we go to do retrieval.